Уважаемые дамы и господа, добрый день. Сегодня мы присутствуем на церемонии подписания соглашения между Международным агентством по атомной энергии и региональной сетью образования и подготовка специалистов в области ядерных технологий StarNet. Для подписания соглашения я прошу выйти на сцену Михаила Валентиновича Чудакова, заместителя генерального директора, директора департамента ядерной энергии МАГАТЭ, и Владимира Игоревича Шевченко, президент региональной сети образования и подготовка специалистов в области ядерных технологий StarNet. Пожалуйста, начинаем церемонию подписания. Передайте, пожалуйста, документы. Я прошу помочь поменять папки. Прошу обменяться папками.
Ведущими университетами и институтами в области ядерного образования. И я сам читаю лекции, сейчас, правда, в записи уже меня ставят периодически, через StarNet. Мы поддерживали и будем поддерживать и рады продлить это соглашение.
Я с своей стороны хочу выразить благодарность Международному агентству по атомной энергии МАГАТЭ за признание статуса и нашей образовательной сети StarNet, и нашего университета, Национального исследовательского ядерного университета, как лидера этой сети и как центр сотрудничества МАГАТЭ, соглашение, о чем мы тоже пролонгировали на следующем годе. Мне представляется очень важным, что образовательные активности, которые мы ведем, в том числе будем вести на площадке Obninsk теха. И здесь в Обнинске, к сожалению, чего посвящено сегодняшнее мероприятие, мы проводим полигоны МАГАТЭ и в тесном взаимодействии с образовательными структурами, это уважаемая организация. И мы будем продолжать делать это впредь, и уверен, что это будет являться залогом высочайшего уровня, качества того, что мы делаем, а через это, конечно, еще и качество подготовки тех будущих лидеров нашей области, нашей отрасли, на чьих плечах будет лежать ответственность за их функционирование в следующем десятилетии. Спасибо.
Спасибо. Dear colleagues, hello. My name is Andrew Gorod, and I will be moderating this session today. So we continue our forum, and now we are starting next session, scientific readings, with a few reports which will be presented in the next few hours. We are planning to finish about 6 p.m. and we will have a coffee break in the middle of the session. Here we are in this hall named after Yefim Pavlovich Slavsky. His photo you can see on the back of this hall. And today we will hear 8 scientific reports. First of all, I would like to kindly ask our speakers not to be so quick in the presentation the reports, because we have simultaneous translation, so it won't be so easy to translate scientific terms. So we are starting, and the first topic for today is that tokamak has to be kept clean. Why it's so important to monitor dust quantity and how to do this. Actually, the topic says for itself what is going to be about, and the author of the report will share his issues and insights about this. And please welcome our first speaker, Mr. Yaroslav Sadovsky, PhD, Associate Professor of the National Research University, MIFI.
All right. Hello, everyone. I'm very pleased to start off this session. And yes, indeed, the topic is how to keep a tokamak clean. But first of all, does everybody know what a tokamak is? Raise your hand if you know. Okay, a few people do, right? But I will quickly remind you. So a tokamak is a fusion reactor for nuclear fusion. It was invented in Soviet Union in 1950s. It has this ring-shaped plasma inside, which is confined by means of magnetic fields. There are a lot of magnetic coils around this plasma, toroidal coils, poloidal coils, and central solenoid. So, as I mentioned, tokamaks were invented in 1950s, and since then, they are developing, they are getting bigger, more expensive, more powerful, but still, they hasn't reached control fusion with positive power output, because there are some problems with it, obviously. So, first tokamak, one of the first, as an example, is a tokamak T6, which was in Soviet Union, obviously. As you see, it is quite small. You can fit it in a room. And obviously, it did not reach fusion. So then, tokamaks were developing, and they were getting more bigger and more powerful, as I said. You can see a man standing near to this tokamak, just for scale. Another example, a more modern tokamak, D3D. You can even walk inside it. You can see a man inside the vacuum vessel of this tokamak, this donut-shaped vacuum chamber where fusion plasma is supposed to burn. But it's not the biggest tokamak up to date. Scientists are building more bigger and more powerful tokamak right now. International tokamak. It's being built in France. It's called ITER, International Fusion Device, and Russia is a full member of ITER team, and actually is providing quite a high part of very important devices for the tokamak and parts for this tokamak. ITER is gigantic. You cannot see a man on this picture, and I will point it out to you. Here's a figure of a man standing there. Yep. Okay. It's like 6 stories high. The diameter of the plasma ring is 12 meters. The volume of the vacuum chamber is about 840 cubic meters. It is supposed to generate 500 megawatts of fusion power, with only 50 megawatts being input into the device for heating of plasma. So 10 times energy comes out. And it will be the first tokamak to reach that. Its cost is already higher than $20 billion, and it's still increasing. So the thing that I want to point out to you is that tokamaks are getting more powerful, more expensive, bigger in scale, and with scale, obviously, all problems also rise up. It's quite convenient to change a tire on a modern car, but if you scale this up, the same problem, but on another scale, possesses a challenge. Same with tokamaks. Every problems of small tokamaks, when scaled up, they possess a challenge. Even manufacturing and transportation, which was simple for small first tokamaks, for ITER is quite challenging. For example, you see a toroidal coil here, one of toroidal coils. And you can see the whole team that manufactured it inside. And of course, it's quite challenging to even to ship this coil to ITER building site. That's how it was shipped. By the way, recently, Russia shipped a poloidal coil for ITER tokamak. And as you can see, it was shipped by sea. There is no way you can ship it by land. So it's also challenging. Another challenge, thermal expansion. You all know that materials expand when heated up. And for small tokamaks, this was not an issue. For ITER, which is gigantic vacuum vessel, when it's heated, it expands something around several centimeters in size, or even tens of centimeters in size. So you have to design special supports for the tokamak that allow expansion of the vacuum vessels. So not only it is very heavy, but you have to support it on special hinges, allowing movement of the vessel. Yet another challenge. And many, many others. But I'm interested with dust. For small tokamaks, it was not an issue. It was generated, but it was not an issue. For ITER, with its scale, dust will be an issue. But anyway, what kind of dust? It's obviously not household dust. Dust is formed in a tokamak when plasma interacts with walls of the tokamak. For example, it could form liquid metal droplets when there is a plasma disruption, so-called disruption, when plasma uncontrollably touches the wall. It could melt the wall, and then metal droplets would form and fly inside the vacuum vessel. Here you can see such droplets on the wall solidified. Eventually, they would solidify and form these tiny, tiny metal balls. And this would be one of fraction of dust we would see in tokamak, spherical metallic particles. But that's not the only type of dust. First wall materials would be constantly sputtered and redeposited on another elements of the wall. And these redeposited coatings would then flake off like old paint. Quite the same phenomenon. As old paint flakes off the wall, in the same way, metal flakes would flake off the inside wall of the tokamak. And that is another fraction of dust we might observe in ITER, metal flakes. And the third type of dust we might observe are dust grains formed when metals would crack under cyclic thermal loads. If a metal is constantly heated up and cooled down, it could form cracks, and this would also lead to generation of dust particles. So now we see at least 3 mechanisms by which dust could accumulate in a tokamak, be generated in a tokamak. But why it is so important? Why it is dangerous? I would point out three possible dangers of dust accumulation. Well, obviously, it's general contamination. There are a lot of scientific instruments inside ITER tokamak, optical diagnostics, mirrors, and so on. If they are contaminated by dust particles, they would not work as they are supposed to. But also, dust has quite large effective surface. It could capture gases, and there would be radioactive tritium inside the tokamak. So dust piles could accumulate this tritium and then become radioactive by themselves, and this would possess a radiation hazard. Tritium quantity in a tokamak must be strictly controlled. That's why dust quantity should be strictly controlled also. And third, in case of an accident, if this dust is blown into air, metallic dust could rapidly oxidate and it eventually lead to a chemical explosion, a rapid burning of this dust in the form of explosion. So these are three dangers of dust, and that's why dust quantity should be controlled on a regular basis. So the thing we are developing at MEFI for the ITER tokamak is the dust monitoring system. But how do you monitor dust quantity? Let's suppose you enter a room and you want to quickly assess quantity of dust in this room. What would you do? You would take your finger, drag it onto the table or something, and look at it. And that's how you get an estimate, a very rough estimate of dust quantity in the room. It's not very accurate, but it tells to some degree how dusty is the room. And that's quite the same thing we would do in ITER. But obviously, we will not do this by hand. We are developing a device to do so. But for ITER, there are a lot of constraints, design constraints that we will have to follow. Obviously, ITER is a nuclear facility, so no human access. It could not be done by hand. Also, there is vacuum inside. Also, there are magnetic fields inside. Very narrow list of allowed materials that we can put inside the vacuum vessel. And we need to collect quite a wide range of sizes of these metallic dust particles, somewhere in the range from 1 to 100 micron in size. And obviously, the system needs to be very reliable, not to break. So when taking this all into account, it becomes quite challenging to build such a system. So obviously, it's not a vacuum cleaner, because a vacuum cleaner does not work inside vacuum, right? It cannot have any kind of complex electronics or motors, because they would not work in magnetic fields under radiation. No cloth or brushes or something like this. And it's highly desirable not to have moving parts at all, because the system should be really, really reliable, and it should be as simple as it could get. So how do you mobilize particles without any kind of moving parts? The answer is quite simple: with electromagnetic field, electrostatics. That's what you can utilize to mobilize particles in vacuum, and that's what we did. If there is a surface on which dust particles accumulate, and you bias this surface, or you bias an electrode above it, it doesn't matter, it's all relative. But let's say we bias the surface positively, and everything around is grounded. If there is a particle on the surface, it would also accumulate this charge. It's a conductive particle, metallic particle. It would also get this charge of the surface. And then there will be two forces acting on the particle. The upwards force, which is the electrostatic force, the field multiplied by its charge, and downward force, which is the gravity. And if electrostatic force is higher than gravity, then particle would be mobilized and will fly elsewhere. That's how we intend to collect these dust particles. Then I would move closer to the real thing. So we have 2 electrodes. But if it's like this, the particle would fly to the top electrode, get recharged there, and then it would want to fly downwards. And then it would just bounce up and down constantly. That's not the way we can collect dust, right? We need to divert these particles somewhere into some kind of collection container. So we modify the top electrode in this way. We do this window blind structure. And then, if the particle flies upwards, it would bounce off these window blinds and flies through them to some kind of container. And that's what we did. We designed this kind of dust collection probe. That's how it works. That's actual results of analytical modeling, numerical modeling of its workings. Dust particles are collected from this plane. They fly upwards through the window blinds, and then they are collected in this region. That's where the collection container would be. That's how it works. So, okay, we established a mechanism on how to collect particles, but that's obviously not all the challenges we had to overcome. Once again, scheme of ITER. We will have to collect particles from this region, the bottom of the vacuum vessel. But then we need to transfer them in this room, which is behind the first bioshield, this wall. Transport them in vacuum, because it's a vacuum extension of the vessel. And then, when collected in this room, we will have to divert these collected containers with dust elsewhere to some kind of lab. So we need to establish a method of transporting this dust probe inside the vacuum vessel of ITER with all that constraints. So for movement of this probe, there are special guide tubes, so-called guide tubes in ITER. They are shown here in yellow. They are already well designed and put inside the vacuum vessel. These are the tubes of like 30 millimeter diameter, like such, through which our probe has to travel. But then, how do you move a probe through such a tube in taking into account all that design constraints? So once again, okay, no complex electronics or motors, no cloth or brushes, narrow list of allowed materials, few or no moving parts, simple and durable. So obviously, this kind of device would not work in ITER. It's too complex. Instead, we took our inspiration from construction workers or from sewage diagnostics. They utilize this kind of endoscopes, flexible endoscopes. And we tried to manufacture quite the same system for ITER. But it's also quite complex. It must fit a high voltage wire inside for biasing that probe. It must be ITER vacuum compatible, so only narrow list of metals allowed. No pockets for dust, so any kind of chain structures would not work. No magnetic materials. It must be rigid enough and yet flexible enough to bend through that guide tubes, but to be rigid enough to push and pull that dust probe. And spool size is quite limited. So the only type of metal we could find for this is titanium tube. It's spooled down on a spool, and then when unspooled, it stays straight. It does not bend when spooled down on a spool. It stays straight, and then we can push and pull our dust probe through these guide tubes. So now the overview of the system is as such. We have this huge spool with titanium tube, which when unspooled gets propelled through the dust, through these guide tubes into the ITER vacuum vessel. We collect dust particles here with electrostatic dust probe we designed, and then we pull it back and collect these dust containers here. It's quite a challenging system with all that design constraints. But we are building it in MEFI right now. Here is the first mock-up of that system. We have this spool with titanium tube, guide tubes, all the way through 2 rooms. We had to make an opening between 2 rooms. It's 1-to-1 scale as with ITER. And we are building it right now, testing, and hoping to get it shipped to ITER and get it working. That's it. Thank you for your attention.
Thank you, Yaroslav. And we have a few minutes for questions. If you have, just raise your hand, please. Yes, please. As you like, English would be better, but you can in Russian.
Okay. Yaroslav, thank you for your speech. It was very interesting. My question is, maybe it's not on your turn, but it might interest you. Are the big tokamak more effective than the smaller one?
Yeah, that's the reason they are designing these huge tokamaks.
So this is the cost of this problem of the big tokamak.
Yeah. Well, there may be other solutions to achieve controlled fusion. Tokamaks are not the only type of fusion reactors, but they are most promising for the current time. Yeah, but maybe there will be another solution.
Thank you.
Передайте слева микрофон вот молодому человеку. You're next. Thank you.
I would like to ask you why titanium tube, not vanadium tube or vanadium tube?
I'm not sure about vanadium, but the unique features of titanium is that it has very low Young modulus and high tensile strength, and it is then very flexible. When we spool it on that spool, it does not deform. That's the unique property of titanium we are using here. Yeah, it's like a spring, you know. Okay. There was a question there over there.
Yes, one more.
Sorry, I missed the first minute, so maybe you already explained it.
Okay. Okay.
But where is this dust coming from? It's environmental mainly, or something that...
No. Yes, there was a part about this in the presentation. It's basically these are products of inner wall erosion with plasma. So when plasma interacts with the inner wall of the tokamak, it slowly erodes it, and this is where dust is generated.
How frequently this procedure will be?
It's a very interesting question, which we are asking from ITER all the time. Probably several times a year.
Okay, so it's not weekly cleaning.
No. It's not cleaning. It's probing.
Okay.
Yeah. We probe the tokamak, then we tell another team, okay, it's time to clean it up, or not.
Any other questions to the speaker? Okay. Thank you very much, Yaroslav.
All right, thank you.
Yeah. We are switching to the next presentation. And actually, everyone has heard about Large Hadron Collider because it's a grandiose science project involving more than 100 countries with 10,000 scientists. But also there could be smaller charged particle accelerators, and they can serve different goals. So our next speaker will be talking about these goals and these smaller colliders, and the report is about collider for everyone. What task can be solved with the help of charged particle accelerators? And I would like to invite on the stage Mr. Yaroslav Shashkov, PhD, and Associate Professor of the National Research Nuclear University, MEFI. You're welcome, Yaroslav.
Thank you very much for introduction. Can you please raise your hands if you ever heard about Large Hadron Collider? Just to be clear.
the Large Hadron Collider, the big machine located in Switzerland, in France, under the ground? No? Okay, who have ever heard about the Iron Man superhero from Marvel Universe movies? Okay, raise your hand if you just shy and you don't want to raise your hand, even if you agree with the question. There will be a little link between these two parts. I really like particle accelerators, and I really like Marvel movies. And one of my favorites is Iron Man 2. In this movie, the superhero Iron Man faces a difficult challenge. His fusion reactor that provides energy for his iron suit faces a problem. The material of this fusion reactor starts to poison Tony Stark, and he will eventually die if he will not find a solution to this problem. For this specific fusion reactor, collecting of the dust is not a problem. So Tony Stark finds a solution. He obviously builds a small particle accelerator in his basement from a scrap material single-handedly in just 2 days. He creates a new material, he replaces the material of his reactor, saves himself, saves the whole universe, etc. I really like and I really hate this scene. I hate this scene because in Tony Stark movie, his particle accelerator was working from the first time. It worked on a first try, and it just doesn't happen in real life. I understand that there is aliens, magic, multi-universes in these movies, but this is just too much for me. But I really like this scene because probably for the first time I have... Hello, everybody. Probably for the first time I have seen a movie where particle accelerator is presented as a tool of creation, as something that can create new materials and help to solve our problems, and not as it usually is represented, where crazy scientists build a huge machine, collide particles, the black hole appears, and we all die. What Tony Stark showed in his movie is much closer to reality, because with the help of particle accelerators we can treat cancer patients with radiotherapy and proton therapy, where with a beam of protons we just burn the cancer tumor that is located inside the body of a human. We can also, with the help of synchrotrons, generate a powerful X-ray sources. Powerful X-ray sources, and look into the microscopic world of viruses and biological samples. And of course, at the Large Hadron Collider, we can study how our universe works at the smallest scales, and to study the laws of physics that were working at the beginning of our universe. But what is particle accelerator? Particle accelerator, it's not me, I'm sorry, it's doing it on its own. In particle accelerator, we accelerate charged particles, electrons, protons, or ions. We accelerate them to the speed, almost achieving the speed of light. And we need not just to accelerate one particle, but we need to accelerate billions and billions of this particle to achieve some useful effects. Despite the fact that particle accelerators is one of the most complex installations that are built by humans, the recipe for every particle accelerator is quite simple. We need just 4 ingredients. We need to generate our particles, we need to focus them, then we need to bend to the trajectory of these particles, and we need to accelerate them. To generate particles, we can with so-called injectors, where, for example, we have a Wolfram coil that is heating up, and with a thermal emission, electrons start to escape the coil and go into the accelerator, where they are accelerated by a ref cavity. Next, we need the bunch of particles can consist of the particles of the same charge, and the particles of the same charge like to repel from each other. In order to compensate this effect, we need to focus them with the magnets, so-called quadruple magnets. If we will use them in our system, the size of our bunch will be the same across the whole accelerator. But without these magnets, our bunch will be quickly destroyed, and probably particle accelerator will be damaged very soon. The next element is bending magnets, with which we can manipulate the trajectory of our bunch of particles, and we can even make the trajectory of this bunch circular, like in Large Hadron Collider. The higher the energy of these particles, if we want to increase the energy of these particles, we need either to increase the radius of the accelerator and make it huge like Large Hadron Collider, or we need to increase the magnetic field strength in the magnets. Of course, in this parameter, we have a certain limit. In this parameter, the only limit is our budget. But this formula is the reason why Large Hadron Collider is so big, because we have big energies and we have a limit on our magnetic field strengths in magnets that we use. And the last part of the accelerator that we need to apply to build this machine is accelerating cavity. Accelerating cavity is just a metal cavity in which we apply a RF power source, and we have a standing electromagnetic wave inside, and by passing this RF cavity, our bunch gets a little bit of energy on every turn, and it's becoming more and more energetic. Each of these parts is developed by a team of scientists that do not work. For example, the specialists on magnets usually know nothing about the accelerating cavities, and the specialists on injectors don't know about the whole machine. But somehow, by working together, these wonderful teams of scientists are able to create these wonderful machines. And with the help of these machines, we are able to achieve great scientific results. First of all, the particle accelerators is a basic machine for studying the matter and elementary particles. On this table, we can see the so-called standard model. Standard model is the most fundamental scientific theory that describes all the elementary particles that our universe consists of. And if you're not a specialist in particle physics, this table probably looks for you something like, the joke is killed. Something like this, which is the same standard model, but in Japanese. So the whole universe consists of these particles, but despite the fact that it is the most developed theory that exists nowadays, it doesn't answer all our questions. It doesn't answer the question where the universe comes from, why this standard model is exactly like it is, what is dark matter, what is dark energy. And in order to answer these questions, we have basically two strategies. We can increase the energy of collisions between our particles, hoping that we will discover some new particles that is not in a standard model. for this, we need to build big, huge machines. And another strategy is increasing of precision of our measurements. So we can build a machine that is much smaller, but it's working in a very specific energy region, but is working with a much higher precision than Large Hadron Collider. For the first strategy, there are several projects. The most famous one, probably, a Future Circle Collider that is going to build, that is planned to build in France as the next step of Large Hadron Collider. It is going to be a collider with 100 kilometers circumference. Another project is circular electron-positron collider that are planned to build in China. The length is the same, so it's very interesting to see which of these projects will be realized first. But if you think that 100 kilometers is ambitious projects, probably with a budget of $20 billion, there is also a project of building a very large hadron collider on the moon. Maybe we will need like technical pass for fixing this stuff, or as you say, or I just continue. I don't know. I think it's just annoying. It's like a little.
Actually, I'm sorry, just as technical issue. This problem with the project causes by the plugs. If anyone is using the plug on the table, please take it off, because it
You know, me and Yaroslav Sadovsky, we are scientists who can build complex machines such as particle accelerators and thermonuclear fusion reactors, but projectors is something else, like printers. They are working on their own laws. So probably it will be harder to imagine a project that is more ambitious than the project of building a very large hadron collider on the moon. Of course, it's more like intellectual challenge than a real project, but maybe our grandsons will be able to realize this project. And idea of the project is very simple. You need, in order for a large hadron collider to work, you need to cool down it to very low temperatures. And it is very low temperature on a moon, so you don't need to spend any additional air energy for cooling. About the small projects, I can say about one example. This is a muon G-2 project in Fermilab in the United States. They have this very specific task of measuring magnetic moment of a muon. And this is an interesting project because in theory, the value of this magnetic moment should be like this, and an experiment like this. And everything agrees very nicely until you go to the 10th digits. For ordinary citizens, there is not so much difference in these two numbers. But for a real scientist, he understands that there can be two explanations. It's either we don't know anything about muon magnetic moment, or there can be new particles that affect this muon magnetic moment. And it's probably the biggest scientific achievement of this year. Nevertheless, I'm really excited about the results because they were able to achieve the very high precision of these measurements. Also, there are two small colliders that are built in Russia currently. This is like Small Hadron Collider, nucleotron-based ion collider facility NICA in Dubna, and Supercharm Tau factory that are probably going to be built in Sarov. Both of these machines are much smaller in case, but they are aimed at a very specific task. And probably here we will find some physics beyond standard model, and it will be a Nobel Prize scale discoveries. So about the radiotherapy, another application practical of accelerators is radiotherapy. With a small accelerator, we can accelerate electrons to a high speed. After that, this beam goes into the target, generates a lot of X-ray X-rays, and with the help of these X-rays, we're starting to damage the tumor, the cancer tumor of the patient. Because of this radiation, we damage the DNA of the tumor, and it eventually dies, and the patient lives. Another technology for cancer treatment is proton therapy. Here, with the help of proton beam, we can destroy the tumor that is located inside a body just by burning it by millimeter. And we also have this technology here in Obninsk in one of the medical centers. The next, the last but not the least application is the synchrotron sources. Electrons have a very interesting effects when they reach relativistic velocities and they go in circles on the orbit of accelerator. It starts to emit synchrotron radiation. And interesting thing about this synchrotron radiation is that it's also in X-ray diapason. And the wavelength of X-ray is compatible with the size of an atom. And because of it, we can, with these X-rays, get a very clear pictures of proteins, viruses, and with this knowledge, we can create new medicines and again, treat illnesses. And another interesting application of these X-ray sources is cultural heritage research. Here we have a scroll from that was burned in city of Pompeii due to eruption of Vesuvius volcano, and it's absolutely burned. You cannot unscroll it, you cannot read what's inside of it. But the ink that was used for scribing on this scroll contains a little bit of particles of metal. And by scanning with X-ray this scroll, we can create a 3D map of distribution of this map of this metal that contains an ink, and we can unscroll it with the help of 3D models like it's presented here. Synchrotron radiation sources have a lot of applications, and currently in Russia there is 4 synchrotron lasers are built. One in Moscow, one in Protvino, which is just 30 kilometers away from here, and another one in Novosibirsk, and another one in Vladivostok on Russky Island. This is not a full list of all the mega science projects that are currently built in Russia, but I have no any doubts that the researches that will be built, that will be achieved on this machine, even the Tony Stark will be quite jealous of these achievements. Thank you.
Thank you very much, Yaroslav. Any questions? Yes, please.
Hello, everybody. Actually, I want to ask you about when you mentioned about Switzerland plants that cost 20 or 40 billion dollars, right?
Mm-hmm.
It's interesting to me to know about how many efficiency that can produce from this plant.
I'm sorry, efficiency?
Yes.
It's not a plant, it's a particle accelerator. So it does not produce energy, it produces knowledge. It produces data about fundamental laws of physics. So here we collide two particles, two bunches, and we collect the data of how they collide. What products are generated in results as a result of these collisions. And by analyzing this data, we can understand how they work, from what they consist of, and deepen our knowledge about the universe laws. So, unfortunately, it doesn't produce energy, but it consumes it a lot.
Thank you.
Next question. Yes. Передайте микрофон, пожалуйста, вот на первый ряд.
Thank you for the talk. Do you believe that the evolution of machines is like that, so they just have to be bigger and bigger? Is there any other way? Is there any like new ideas to make like a fusion machines, fusion colliders?
It's a great question. Of course, I truly believe that we do not need a collider on the moon, and that we do not need a 100-kilometer collider in Switzerland or in China. Because, of course, there are I strongly believe that we need smaller machines aimed to increase of precision. And concerning about the technologies, alternative technologies, yes, there are alternative technologies for accelerating of the particles, but they work very poorly right now. There is so-called plasma acceleration, with which we can achieve 1,000 times more energies on a scale 1,000 times smaller. But this technology is so experimental, and the results that are produced in these machines are how to say it's differentiate from one time and another. In a Large Hadron Collider, you have like stable results. You have this beam with these parameters, and for elementary particle studies, you need a high precision of this. Probably maybe in 30 or 40 years, we will invent some magical plasma acceleration, and it will work reliably, and we will not need these huge machines. But right now, I think we need to aim like to all technologies, but for a smaller scale.
Thank you.
One more question, yes, please. Let's start with you and then switch to you. And the third one.
Hi. Thank you for the presentation. I have a question more, let's say, you as a person having browsing all these different accelerators, having working at CERN for 12 years plus, and if you have to say, give some advice, or what would be better to apply some of these resources, would be more in physical precision, maybe this was already the answer, or going for these very large dark matter searches, etc. Obviously, there is always the romance to find what that matter really is, but if in terms of the efficiency, in terms of the science, would be you more entitled to say, I would prefer to have a very high precision electron collider to measure this difference? What will be your approach in that sense?
So the question, what should we fund?
The guy will decide if this is the regular. You tell me which one you will go for.
So the question is, should we finance a small accelerators or a big one? I honestly believe that this is a little bit wrong questions. I think we need to fund Large Hadron Collider and build smaller machines, because it's not like zero-sum game where it's either this or either this. Or like, what will you finance? Education or medicine? It's said I think that there is a plenty of money in the world, and we can finance for both. But in terms of, if we will rephrase this question in this way, which machine, the Large Hadron Collider or a Small Hadron Collider, which one will achieve interesting scientific results sooner? And I think that the smaller machines will provide the smaller new results faster than the large one. And but it's just
Besides the construction side, right?
Hmm?
Besides the construction side.
yes,
Good,
yes. However,
Could you please pass the mic here? Yeah.
Спасибо большое за доклад. Небольшой вопрос. Вы говорили, что можно использовать ускоритель частиц для анализа археологических находок, но насколько это вообще целесообразно, если можно использовать рентгенофлуоресцентный спектрометр, который в миллион раз дешевле и, по сути, даст те же самые данные?
thank you for the question. I think this is quite specific questions for the users of this machine. But I will say that synchrotron sources are constantly used in these types of analysis. Even the Louvre in France, in Paris, it has its own small accelerator for research of pictures. And if I'm not wrong, the Mona Lisa picture was analyzed by this machine. And recently in Kurchatov on a synchrotron source, there was studies of remains of Ivan Grozny. They were brought there, and some interesting results were produced. Probably the answer why this is not possible is because of the quality of X-ray rays that we are producing in synchrotron source. In synchrotron source, they are all the same wavelengths. They are very powerful, and you can make variations of energies as you like. And it brings you a broad broad possibilities for studies of different materials. Like, for example, what is colors of paint made from the picture, and what Ivan Grozny was having for his last supper the day before he died, and etc., etc.
And the last question to this presentation, please.
Kind of like two questions. The first question is, what is the probability of fusion inside the same collider? Because these particles are also moving at a certain high speed. So what is the probability, instead of them splitting, they end up fusing together? Then also, you spoke something about radiation. Like, can you explain more about the formation and the type of radioactive particle that we are talking about?
About fusion in particle accelerators. Look, for a fusion process to happen, we need energies, please correct me if I'm wrong, about 1/10 of kilo electron volts. In Large Hadron Colliders, the energies are 1 billion times higher than energies that are required for fusion. So it's imagine you like trying to put a nail in a table with a hammer, and you just smashing it with a very big hammer. There will be nothing left from the nail, probably. So particle accelerator is so much beyond of energy necessary for fusion. So maybe there is some, but it doesn't matter. It's not such a big problem to achieve these energies in particle accelerator. For the fusion, there is a problem of making this energy production efficient and reliable and economically beneficial for everybody. And the second question?
Передайте микрофон для второго вопроса.
I was asking about the type of radioactive materials, like when you're talking about the proton accelerators.
Radioactive materials, which there is a lot of radioactive materials in particle accelerators, like in targets or in an area of detectors, a lot of stuff. And some parts of accelerators are becoming quite radioactive after the decomposition of the machine after it starts work, and you need to utilize it with all the necessary precisions as it happens in nuclear reactors and everywhere where we have such.
Like what type, like tritium or like what type of? Okay,
Okay. What type of particles we accelerate in Large Hadron Collider? Usually it's hydrogen or plumbum, lead, or gold, or some. It really depends from a machine. In Nika Collider, they accelerate gold. In Large Hadron Collider, they accelerate lead. There is a lot of reasons why they're choosing this or that material.
Okay. And the last short question, please, and we'll finish.
So, sir, you mentioned using the proton ray and the X-ray to destroy a tumor in the mind. So, how do you ensure the safety of the mind while using the ray?
It's a good question. First of all, this is already developed technology. It's used for 50 or 60 years routinely. It's radiotherapy is one of the three main methodics for cancer treatment with chemotherapy and surgery. Also, there is radiotherapy, and they always go in a combination with each other. So there is not something like you prefer this one or that. It's the decision of the doctor who knows the patient much better than some particle accelerator physicist. There is a lot of safety measures. It's really a long topic, and I think we are already out of time. But I will just mention that we fixate the patient with special masks, so he doesn't move. The X-ray is emitted from particle accelerator only when the patient exhales, so we know the position of his organs, and there is a lot of more methodics to ensure the safety of the patient.
Right, thank you so much.
Thank you, Yaroslav. Actually, the coming coffee break is a good place to continue into details. And I would like just to remind kindly not to use electric plugs on your tables because it's connected to our screen and projector. So the next report is charged and spinning on solving the equation of state of electrons in the solenoid fields. And the author will present a method of constructing solutions to the two-dimensional Schrödinger equation for a charged spinning particle in a varying magnetic field. And I would like to invite Mr. Stanislav Baturin, PhD, leading researcher and assistant professor of the Physics and Technology, Mega Faculty at Edinburgh University.
Colleagues, thank you so much. I'm really pleased to give a talk here. So, well, yeah, I'm going to talk about the Schrödinger's equation, so I'm going to switch gears and talk math. Well, I hope it's not going to be that complex. So first off, you said, you'll just ask me, Schrödinger's equation and magnetic fields, like, are you kidding me, right? So, because the solution is long known. Landau solved this problem long ago, so what should we discuss here right now? All right, it's... well, it's easy and not that easy at the same time. First off, let me just give you a brief outline of my talk. So first, I'm going to talk about the twisted states. It's something that is really interesting and which attracts a lot of attention right now, twisted quantum states. And they're tightly connected to these magnetic fields and electrons and magnetic fields and such and such. Then I'm going to talk about like which exact problem we're going to solve. And then we talk about a bit of a so-called rectification theorem. It's something from a differential equations, but I'll try to make it simple. And then I'm going to talk about some mappings and then the application actually to the so-called Landau states or to the states of the electron and the magnetic field. So what kind of a new insights we can gain out of this math that I'm going to talk about right now. So first off, the twisted states. What kind of a beast is that and what I'm going to talk about. So the twisted quantum states are kind of very simple. So we know that there's such thing as a plane wave. The plane wave has a plane wave front, right? So it's known to almost every physicist. But along with the plane waves, there are also cylindrical waves. It's just a different solution to the wave equation in 3D. But the thing is that they're kind of like completely different from the plane waves. And if you look at the wave front, so the wave front of such a wave is a spiral. And it's a kind of funny and distinct feature, but so what's about it? So along with this like spiraling wave front, you have a so-called angular momentum, a projection of the angular momentum. So indeed, this wave have a kind of twist, so it kind of rotates along the propagation axis. So for instance, if we're talking about the light, if I illuminate with this light some small particle, we all know about the pressure of the light, right? So if you illuminate something with a light, then the light has the pressure, right? You can sense the pressure of the light. But if you illuminate something with a twisted light, we'll sense not only the pressure, but the momentum. So it will rotate the object that you illuminate. That's a kind of really kind of fun and interesting feature of this particular state. Interestingly enough, the photons are not the only waves that we know, right? And just because of the duality, all particles, because particles are waves, can have these features. For instance, electrons also could be considered as twisted waves, and it's all the same. It's the same as light. So if you look at the intensity profile of such state, so you'll see that they kind of have these donut shapes, and depending on the quantum numbers, actually the amount of the momentum, of the angular momentum that this state carry, have a different structure. So it could be like one donut or like several donuts and such and such. Here I have two references, just if you will have access to these slides, you can read more on that. And you can, there are two nice reports that have a really brief reviews of all that stuff. Both states, in both cases, the waves are explained by the means of these functions. They're kind of like a bit scary, but like, look, so we have this like transverse part, which is in cylindrical coordinates, it's just the Laplace operator, and we have this longitudinal part, which is just the first derivative by z. If you look at this formula, it will probably remind you of the Schrödinger's equation, because this part is just the momentum operator, and this is some kind of a time derivative. The solution is like that. So it has these Laguerre polynomials, these exponents, and everything depends on z coordinate here. So you have this size here, and you have this so-called the wavefront curvature, and you have a phase factor, which is here. So the Landau states, like long ago, Landau solved this problem for the electron in the magnetic field if you have a uniform magnetic field. And it's kind of not really connected to what I've showed you before, because that was something different, right? But if you look at the equation and at the solution of this equation, it basically resembles the same formula as for those twisted states of light and of the twisted free electrons, if you want so. So basically, the Landau states and twisted states are kind of the same beast. And that's kind of the question. So how you connect those two things together, and that's what I'm going to talk about today. So how you connect kind of old stuff that is known with some new ideas and some new, well, research field, which is kind of booming right now. One important feature that I'm not going to really talk about today, but I really want to mention, that the orbital momentum is so-called topological charge. So to make it brief, what the topological charge is, it's some sort of a number that if you put into your state, into your quantum state, it will never disappear. So it will always be there. So it's some sort of a structural, if you want so, structural number that you can, well, you can only like either insert or remove. So it kind of responsible for the shape and for the, again, the transfer structure of your wave. So once it's in, you can never remove it out of. And the orbital momentum and the topological charge, as Barry told us, it's kind of the same. Well, let me switch to the problem and let me talk like what we're trying to do right now. So actually, so now if we know that in a free space, it's a twisted wave, and inside the magnetic field, it's a Landau state, how we can bridge those two states together and how we can answer the question like whether it's possible for the electron to transit from the free space if it's twisted into the magnetic field and being captured directly into the Landau state. Well, first off, we'll start from the Dirac equation. And we know that the Dirac equation could be reduced again to the Schrödinger's equation if the field is uniform. And this transformation is called Foldy-Watt-Heise transformation. But let me just say that. So you can do like some trick and you can again transform your Dirac equation again to the Schrödinger's equation that I showed you on my first slide. And in the end, what we're going to do, we're going to solve this problem. And this problem is kind of well known. So it's a harmonic oscillator. You have like momentum squared sum, coordinate squared sum, and the projection of the orbital angular momentum operator, which is basically the which connects those two oscillators. So how are we going to do it? Oh, one more thing. Previously, I showed you that it was just a harmonic oscillator, but just because I can insert those terms here. Those are the dissipation terms, so I can actually account for the dissipation in the quantum problem as well. Just for the generality, because I mean, this problem could be solved as easy as the previous one. How are we going to solve it? Well, interestingly, the solution of this quantum problem goes back to, well, a classical idea, and this idea is so-called the rectification theorem. It's you can find it in a well-known book by Vladimir Arnold. It's on the differential equations, and Arnold says that in his book that this idea goes back to Newton. So basically, the solution of a quantum problem goes back to Newton. Okay, so what's the idea? Okay, the idea says that if you have a, say, differential equation like that, you can make a substitution of variables such that in the new variables, for instance, here it's t and y, all solutions will be just constants. Basically, you rectify locally the vector field of your equation. Okay, it doesn't give us much, right? So you have to know the solution of your equation, and then you can do the substitution. Well, yeah. But if I'll switch to, well, a slightly more complex problem, then what can I do? So I'll take the harmonic oscillator, do a substitution, and this harmonic oscillator with the friction and the force could be reduced to just a free particle motion, right? Look, this equation corresponds to the Hamiltonian. And this means that this transformation transforms the Hamiltonians. And this is interesting, because in the quantum mechanics, we work with the Hamiltonians, with the Hamiltonian operators, right? So that means that this transformation can transform Hamiltonians. And if I'll just add hats to this H, well, to these H functions, there will be operators. And we can go to the quantum mechanics as easy as that. So this trick is called the quantum Arnold transformation. So basically, I'll do the substitution and pose a question. Can I transform a Schrödinger equation for the free particle to the Schrödinger's equation of the harmonic oscillator? Well, the answer is yes. So first, I'll do the substitution that I showed you before. That's the solution of the classical equation. But in quantum mechanics, well, you have to account for the phase of the wave function. And interestingly enough, just because like everything that is happening when I do this substitution, I have the shift in the momentum, then I can easily find the phase. And this trick is called the, well, this guy is the gauge potential, and this is the phase caused by the classical gauge potential, which again comes from just the classical transformation. So, finally, the transformation will look like that. So U1 and U2 will be the solution to this harmonic oscillator, to the equation of the harmonic oscillator, a classical equation. So it's not a quantum equation. And I'll do this transformation of time and coordinate, and will account for the phase factor that appears just because I shift the momentum. And this operator will transform, okay, so I jumped too fast. This operator will transform my free equation into the harmonic oscillator equation, Schrödinger's equation. Well, I can go back and forth because like you can show that this is a unitary operator and this operator is unique. So that means that there's a, well, one-to-one correspondence between those two systems, which is kind of cool. So you can make a step further and connect two harmonic oscillators, and by just composing those two transformations. So H here is the harmonic oscillator with omega 1, and HT it's with omega 2 and the different friction coefficients. So if you compose them, you can build a composed transformation, which we call Yermakov transformation. And here you have a very simple equation for this B coefficient, which basically is the main coefficient in this transformation. So this means that now I can, if I know the solution inside the magnetic field or say in free space, I can easily solve the problem by the transformation. So if I know the wave function, then I just need to solve a simple classical equation, and I know the evolution of my state. And this is, well, as simple as that. So before that, we started from the non-stationary quantum problem, and we were able to reduce it to a, well, to a solution of a, well, non-linear, but a very special non-linear equation. This equation, by the way, is called Yermakov equation, and it allows exact solution. So it's so-called integrable equation. So despite the fact that it's non-linear, you can solve it exactly in many special cases. The Landau states, what we can learn about the Landau states, long known states, that was derived by Lev Davidovich. So just to recall what those states are, that's the harmonic oscillator, the connection. So the magnetic field is constant, it's time independent, and the solutions could be written down in this form, as I showed you on one of the first slides. Instantaneously, if I will map this system on itself, just for fun, you'll see that Landau states are not the only solution to the Landau problem. And you have, on top of just stationary states, which was derived by Lev Landau, you have non-stationary states that looks slightly different. So what's the difference? The difference is that the average values calculated on these states will differ by this B coefficient. And B, again, is the solution to this Yermakov equation, which is not necessarily constant. So it basically depends on time. So this problem allows, say, oscillating solutions. If the solutions oscillate, then the classical multiple electric moments oscillate as well. And in this case, those solutions must radiate. Let's look. Let's look at the example. So what is happening? So if I'll just solve this equation, then this parameter that describes basically the size of my packet. So it shows that, okay, in free space, it expands, then it oscillates inside the magnetic field, and then if I'll choose the parameter the right way, I can capture the packet exactly into the Landau state, but that's a very rare case, so it's practically impossible to capture the packet. So the oscillations will always occur. As for the energy looks always also funny. So if the packet goes from the vacuum into the lens, the energy goes up. And that's because as I said, just because you have the oscillations, and the oscillations will cause the radiation. So, well, I know that was a bit fast, but to conclude, what is the point of all these tricks? So, look, we started from the quantum problem, right? So, and I briefly showed you how a very simple idea of Newton, right, could be applied to the quantum problem, and shows you the essence of the evolution of the quantum problem, which is actually classical, right? So we've learned that the solution of this problem, could be found through the classical equation, which is a bit, which may seem complex, but, it's just one simple equation instead of the Schrodinger's equation. And this simple equation is just for one parameter. Well, that's basically it. So I want to mention that we've recently done this research with my student. And if you want to learn some details about that, you can read this article. Other than that, thank you so much, and I'll take any questions right now.
Thank you, Stanislav. So, questions?
Yeah.
Uh-oh. It was too difficult.
It was tough. I'm sorry.
Yes. Yeah, for sure.
Okay. Thank you very much. Are these pure theoretical studies, or maybe there are some experimental studies where they do observe this kind of spiral wave fronts and so on?
Thank you for the question. Yeah, sure. So the twisted light is observed and routinely achieved at the lab. So it's something which people know how to do for years, actually. So as for the electrons, so they can achieve, but at low energies, those twisted electrons. So this is something that people can do experimentally as well. Some particular features that I was discussing right now, I don't think that they observed some of them, but it's not that difficult to try to set up an experiment and to figure out if this theory works or not. Well, I believe it works, but Thank you.
Thank you very much. May I ask you the following question? Can your approach or can your method be applied to another geometry? So if the magnetic field is not along the propagation axis of the discipline?
Well, yeah. You may do the same trick. So the idea here is in the substitution of variables. So yes, you may, but a little bit of math, a little bit of work, and you can apply it to a different problem. So the magnetic potential have to be linear. Other than that, you can do the trick.
Okay, so it means that you somehow solve analytically all the behavior of twisted light in any kind of magnetic field.
Well, not light, but electron. Well, maybe.
Okay.
Thank you.
Thank you.
One more question? Or no? Okay, Stanislav, thank you very much.
Thank you.
One more?
Yeah,
Someone is ready. Okay.
In your opinion, can we use this method in controlling the combustion process in combustion chamber? We have a lot of problem with this combustion chamber. We can use this method in it?
Wow.
In your opinion?
That's a very good question. Maybe, I don't know. I haven't thought about that, but maybe.
Thank you.
Thank you.
next questions will be during coffee break, I guess.
Oh yeah.
Thank you, Stanislav.
Thank you.
So we are switching to the next presentation, and it will be devoted to the production and application of isotopes for the scientific field. And the report "Isotopes as Researcher's Toolkit for the Third Millennium" will be presented by Mr. Vasily Karnaukhov, PhD, Associate Professor of the National Research Nuclear University, MIFI. Vasily, you're welcome. Вот, это
Good afternoon to everybody. I'm glad to be here. I'm glad to be here and present this talk about isotope as a toolkit for the research of the third millennium. I will focus only for application of stable and radioactive isotope in particle physics. So let's start with the definition. In 1913, English radiochemist Frederick Soddy proposed the concept of isotope of atom. He won Nobel Prize in Chemistry in 1921. And what isotope is isotope are varieties of atom of the same chemical element that have the same nuclear charge Z, but different atomic mass A. So the term isotope was proposed again by Soddy in his paper published in Nature in December 4, 1913. In red, you see here, you see here the very in bold statement. From the point of view of practical application, few discoveries of the 20th century can be compared with the discovery of isotope. It's true. I will demonstrate you some application. And what's more about isotope, it's nuclear properties of isotope differ radically. For example, the two lithium isotope 6 and 7, absolutely different from point of view of neutron cross-section, for example. But the chemical properties of isotope of an element are similar. Here is the list of some isotope you heard about them from americium 241 until cobalt 6 and so on. So, pardon. Okay. So, the subject of my talk is particle physics as a big customer of stable and radioactive isotope. First part is a double BTDK experiment, which need hundreds kilograms of certain isotope like xenon 136, moly 100, and germanium 76. And next topic is calibration of solar neutrino detector and investigation of neutrino properties. For example, sterile neutrino using a low background detector placed deep underground, and intensive neutrino source based on argon 37, chromium 51 isotope. So let's start with some introduction, theoretical introduction of particle physics. Here you see the standard model of particle physics. There are quarks here. You see a lepton. And also particles which force carrier boson, so-called boson. But everything here is fixed, and physicists, most of physicists are happy to have such a situation, except only one situation with neutrinos. You see, if you can see here, there is one unpredictable value. It's mass of this particle. Never mind which neutrino, electron neutrino, muon neutrino, or tau neutrino. Here you see only just limit, and to very small limit. Why? Let's move further, and I would like to remind you that this very strange particle were introduced on the tip of a pen by a very famous physicist Wolfgang Pauli. He's a real inventor of neutrino. This is very rare situation where we know exact date of birthday of particle. He wrote some famous letter. He introduced this particle with very strange properties like massless, no mass, no charge, and other very strange characteristic, just to explain the situation with conservation law of energy conservation in beta decay process. But starting from this date, there is always big attention to this particle from scientific community. In 2015, Nobel Prize was for discovery of neutrino oscillation, which shows the neutrino have a mass. It means physics beyond the standard model. So, in 1930, no mass. 8 years ago, we observed some mass indication and so on. So, in reality, everything are linked to neutrino. It's something like Pandora box, which we opened some years ago. Question for neutrino physics. There are three. First of all, why so tiny neutrino mass? Neutrino mass and mass hierarchy. Direct or Majorana nature of neutrino. If neutrino double beta decay process exists or no, we will discuss this point. And CP evaluation, why matter dominant in the university. So, in 1935, Maria Geppert-Mayer proposed some very interesting process of decay, beta decay, double beta decay. When the emission of two beta particles, two antineutrino, possible when energetically forbidden simply ordinary beta decay. This is a second order magnitude process, so the half-life is very long, 10 to the 18 year. It's allowed everything according to standard model and characteristic. It's even nuclei. There are 35 isotope. In the nature, we can proceed with such type of double beta decay. So, but 2 years later, Ettore Majorana proposed his new theory of particles. He introduced some very strange particles like that is own antiparticles. You can distinguish particle and antiparticle. It's Ettore Majorana. This particle now, the name is Majorana particles. And the same year, Giulio Racah, also very famous Italian physicist, proposed a new type of double beta decay, but without emission of this antineutrino, just emission of two electron, two beta particles. In reality, it's forbidden in a standard model, but if it exists, there is a new physics, and it's a most interesting situation in modern physics. And there is some statement here. The observation of zero double beta decay process strictly prohibited by standard model. Why? Because there is a this lepton number break of low conservation of lepton number. You obtain, after this process, you obtain just 2 beta particles in the university. It means a new standard physics. So, how to detect this process? First of all, this is a very rare process, 10 to the 25 year of half-life. If you compare with half-life of uranium-238, it's just 2.5, 10 to the 9 year. It's many order magnitude slowly. And if you take 10 kilo of moly, for example, molybdenum 100 isotope, you will measure just 4 events after 1 year of observation. Very rare process. What it means? It means to proceed with new experiment, you need ton scale of a stable isotope, like, for example, molybdenum 100, ton scale, and also very rare, very pure material. There is an expression, radioactivity in banana. If you consume 1 banana, it means you consume 15 becquerel of activity, 50 decay per second. And our material in our experiment should be the level of radioactivity 10 minus 11 becquerel per kilogram. Extremely low. It's a real challenge. So there is a number of isotope we can use to look for this process. It's so-called golden isotope. Here is a list of this isotope. And what's important, you should have some money to buy such an isotope. And the only cost-effective process for production of a stable isotope is centrifuge. And you see this in red. There are several isotopes: moly 100, selenium 82, germanium 76, and germanium and xenon 136. We can use in big scale because of possibility for production with centrifuge. Again, about this process, how slow this process is. If you look at this very famous photo, this is a Big Bang expansion of our university, and we believe the age of our university is something like 13 billion years. If we compare with the half-life of neutrinoless, the double beta decay, it's really 15 order magnitude difference. Very slow process. Here is a list of isotope, promising isotope you can use to proceed with new generation of double beta decay experiment. Here table present first column, it's experiment, ligand, ENEXA, qubit, and so on. Second column, it's isotope you can use. Here it's mass. If you can see the mass, something like 100 kilograms or tons. And in reality, this experiment in the phase of development, IND in progress. This is, for example, Legend is in progress. We are starting this experiment and so on. What's about cost? Cost, it's not so easy question for physicists because it's a government program to support this science. Cost of one kilogram of isotope, or 1 gram, for example, it's for germanium 76, it's something like $80 per gram. It's more than the cost of gold. For example, for cadmium 116, it's $180. And so on. It's really very expensive material. But what's about interest of the scientific community to this to search for this process? Here is the list of experiment which are now running or planned. In total, according to this table, 35 experiments now in a stage of development, of running, and so on. Here is the geography of this experiment, as you can see, everywhere in the world. So I will tell you a short story about one of experiment, so-called Gerda collaboration. It's from 2003 and finished 2016 because now we're starting a new phase, legend, based on this facility. In total, 16 institutes participated in this experiment from Europe, and more than 100 members of this collaboration from Russia. We have Dubna Institute, Kurchatov Institute, ITEP, Institute for Nuclear Research. What's about enrichment? Again, regarding this, it's very easy to understand why we need enriched isotope to look for this process. Natural abundance of germanium-76, just 7.6% natural abundance. And if you will build the facility with this isotope, you need, for example, 11 diode, but if you enrich this isotope to 86%, you just build only one, and here is some equivalent between detector based on enriched isotope and detector based on natural isotope. This is the reason how we about production of enriched isotope. There is centrifuge plant in Zelenogorsk, ECP electrochemical plant in Russia, in Siberia. Here you see one unit of centrifuge which separate isotope. The principle very simple. Left sketch it's a simplified version. Right sketch is more complicated. Let's look at the simplified version. We see there is some cylinder under vacuum with very huge rotation. Rotation is 1,500 rotation per second. Enormous high speed. And you have acceleration half million G. You have some niche of isotope, natural composition. When this cylinder rotating under such a speed, there is some axial gas circulation. There is some radial distribution of different mass of the same element, and you can take light fraction from this place or heavy fraction from this place, but one centrifuge is not enough to get some enrichment enough for purpose of your request demand. You need something like hundreds or even thousands of such a unit, and here you see the photo of this plant with many hundreds units combined in some cascade. By the way, about operation life of centrifuge. When you start to rotate the centrifuge, they never stop. The centrifuge never stop, and the duration of half of operation life something like 30 years. You can compare this guarantee Mercedes-Benz on another car. You see the centrifuge real change. So this is another example of this process. In parallel, we enriched isotope on germanium isotope, germanium-76, but also depleted on another light isotope. Why? Because there is a cosmogenic activation of your material on the above ground, and you need to avoid this activation because you create some this activation from cosmic rays create long-lived dangerous radioactive isotope. And first of all, you run experiment deep underground, and Also, you should keep this material during production well under some shielding to prevent this activation. On the side, there is a special shelter electrochemical plant which just they keep my material after production under protection to avoid this activation. This is some characteristic of this shelter. So it's for former bomb-proof shelter. Also, as I mentioned, your experiment are deeper ground. This is our current experiment in Italy. There is some tank filled up with liquid argon. Here you see this is the germanium detector hang in this cryostat. Another protective material is water tank, and everything deep underground look like Russian matryoshka. So and here is some stage of construction of this facility. It's a really great deal. But also to deliver this material, enriched material from Siberia to Europe, we designed some special 15-ton shielding container to prevent activation. So here some very celebration of successful completion of big undertaking when we produce in Siberia and deliver to Europe this enriched material. Now it's the situation today is Gerda detector. Now we have 200 kilograms of enriched germanium-76 material. So this is a story about stable isotope. Another story about radioactive isotope. Unfortunately, I have limited time. So just there is a detector, chemical detector, which detects the flux of neutrino from sun. We know that the sun generates energy because of thermonuclear reaction, and the evidence of these reactions neutrino flux, and we used gallium detector. It's focus gallium detector, 50 ton of gallium metal inside this chemical reactor. They just share between seven such a facility. Here is a cross section of mountain in Caucasus, deep underground, 3.6 kilometers far from exit of this tunnel. This is a photo of this hole, experimental hole. But why we need here the radioactive isotope? Just to check if your procedure works very well. It's a radiochemical detector. You never fix the exact moment of interaction. It's integrated detector. You should demonstrate that all your procedure okay, and for that we use neutrino source, very high intensity, just to check chemical procedure in this gallium-germanium neutrino detector. This is a general scheme of such an experiment. This is a tank with fill up with gallium metal. Here is this calorimeter with this two type of neutrino source we used to calibrate. One is chromium 51 isotope. It capture isotope. It's emit monoline of neutrino. Another radioactive isotope argon 37. It's emit another energy, and we just produce these two isotope. First it's chromium 51 with intensity half million Curie. It's enormous high intensity, and another source argon, it's 0.4 million Curie. Just to create in the gallium metal neutron flux 2 order magnitude higher than flux from sun. So we used to produce this source. We use 2 breeder reactors. One breeder reactor BN350, another BN600. It's cross-section for photo of this reactor. All the job proof feasibility of this production of this radioactive source was done here in Obninsk, in IBD. It's how to say, it's a male designer of fast breeder reactor in the world, it's IBD, Obninsk. So this is some scheme how we produce chromium source. We just use standard fuel assembly, remove uranium fuel, put inside zirconium hydride. It's moderator like water, and form inside this radiation assembly thermal flux, because actually fast breeder reactor is fast reactor, it's fast neutron, and to get chromium 51 you need to moderate neutron to thermal to transform to thermal spectrum. So what have we done? First of all, we enriched chromium with centrifuge. Some quantity of chromium, half kilo. Then we irradiate this chromium, enriched chromium with reactor in this very special facility and get half megacurie source. Another approach to produce argon-37, we use another reaction, so-called N-alpha reaction. We use calcium compound, calcium oxide, 96% of calcium 40. There is N-alpha reaction for fast neutron. It's okay for fast breeder reactor. It is using BN600 reactor. We produce 0.4 megacurie argon-37 neutrino source to calibrate radiochemical detector maximum neutrino observatory. The scale of this job, we put inside 330 kilogram of calcium oxide inside reactor, fast breeder reactor, remove it, and get about 10 liter of argon gas, argon-37 radioactive gas. So this is I would like to, during this short lecture, just to give you some view how stable and radioactive isotope use in particle physics, especially with this search for neutrino less than double beta decay, or calibrate radiochemical detector of solar neutrino detector. Thank you very much for your attention.
Thank you, Vasily. As we run out of time, we have time for one question. Important question. Do you have any? Yes, please.
in Russia we used centrifuge technology. It's cost-effective technology, and with this technology, first of all, we enrich uranium for production of fuel, nuclear fuel, but also stable isotope. The primary customer is particle physics, because 100 kilo, even ton of isotope necessary for the search for neutrinolysis double beta decay. This is, and also, but this centrifuge technology, you can enrich only element which form a compound with pressure under room temperature, something 10, 20, 100 millimeter of mercury. So it's not all table of Mendeleev tables, but there is another facility in Russia. It's electromagnetic facility SU-20 in Lesnoy, Ural region. It's electromagnetic separation. You can enrich everything you want, but with very high cost. Cost something like $10, $100 per milligram. For centrifuge technology, it's something like 10, 20, $100 per gram. It's 3 order magnitude difference. About something new. Of course, there is another technology of separation. It's well developed in lab scale in Soviet Union, in Russia, but nobody invest money to build big enough facility to proceed with such technology. Now there is only three technology. It's centrifuge, electromagnetic, and also for other concerning other technology, it's how to say. It's question of money, investment of money, and unfortunately, I can discuss this point because no time. Maybe we will discuss in coffee break, during coffee break. So this is a real situation with production of isotope in with centrifuge technology. By the way. Also, ECP, Russia produce stable isotope for atomic power station, like zinc, depleted zinc 64 isotope, 100 kilogram scale. It's some additive to first loop of cooling to water to prevent some corrosion and to save some time for during maintenance. It's also very big customer, and main customer is United States. By the way, it's one of the reasons why there is no any pension, any how to say sanction against Rosatom, because Rosatom supply in huge scale everywhere in the world isotope.
Thank you, Vasily. I think we can continue during coffee break with the additional questions. And before leaving for coffee break, I would like to pay attention to the Russian-speaking audience. Tomorrow in this hall, there will be youth scientific technological conference.
We see education as a key factor that impacts the future. It's beyond Rosatom, beyond nuclear, and even beyond energy. It's the matter of our generation.
We now have the largest generation of young people in the history, with only 46% employed. In sub-Saharan Africa, more than 70% of people are under the age of 30.
Worldwide, only 32 countries operate nuclear power plants, and the rest, 161, don't. That's the same world where 2.5 billion people cook with wood.
We witness a lack of general knowledge about how nuclear energy works and also basic energy knowledge in Brazil.
In total, there are only 2 universities in Uzbekistan where you can study nuclear energy.
Nuclear energy is often portrayed in Argentina as a technology available only in the developed countries.
So as humanity, we have all the tools and the advanced technologies that we need in order to solve our problems related to energy. But it turns out that the main problem we face is lack of literacy and various misconceptions at all levels.
To educate people on clean energy future, we should work with what I call 5 Ps, and those are policymakers, politicians, public, professionals, and press.
First, policymakers should switch the paradigm. That is, focus on the economic risks from continued reliance on hydrocarbons. As Impact Team, we believe in order to increase our impact, we should be building a worldwide education ecosystem and transform Rosatom's competence centers into public knowledge hubs accessible for all.
Achievements and multi-sector expertise that Rosatom collected throughout the years have stepped beyond power of nuclear, while it has always been a core. Why don't we invite everyone to dive into this ocean?
What if there is no knowledge hub in the nearby?
There should be an online platform connected to all centers around the world that provides necessary reports, workshops, training, and expert advice from Rosatom, business, academia, public and private entities, as well as NGOs. The first knowledge hub is already there, and young people in the city of Nizhny Novgorod have a common place to exchange ideas and learn more about atoms and how they can make people's lives better.
This is how we see the future of education for Rosatom as the younger generation.
How do you see education by 2050?
Whatever changes come on the way, there are values that remain the same. Education is one of them. For almost 80 years, Rosatom have been creating conditions for all generations to reach their potential. Rosatom Skills Academy brings together the best of educational experience and makes it available to the world, adding the innovation, making knowledge and top professions available to people from early age to mature specialists. Protecting business by providing projects with qualified personnel and talent support and development in decent work for economic growth. Supporting regions and communities. Rosatom Skills Academy ecosystem integrates education, digital platforms, quality management, practical component, and supportive communities. All those contributing, from school education to colleges and universities, and further to lifelong learning, from a specialist to a working family. From the bravest dreams to the highest achievements. From a plant to the society. From lighting an interest in science to the burning desire to create, through the efforts and labor of one to well-being of many. From a better today to sustainable future. Rosatom Skills Academy, empowering one.
Сообщество.
I hope you had a great coffee break and now we start working again. So, what do weather forecasting, the Egyptian pyramids and the search for running ore deposits and the nuclear industry have in common? This answer is possibly using of cosmic rays and to solve all these issues. And I would like to present our next speaker with the report Months of Cosmic Rays as a key to the heart of the reactor and the secrets of the Egyptian pyramids. Please welcome Mr. Igor Zadeba, PhD, Associate Professor of the National Research Nuclear University, MEFI.
Good day, my friends. So, nuclear physics is not limited by nuclear reactors and all that is connected to nuclear technology, and also it's also a part of elementary particles physics. Cosmic rays is also an important part of modern nuclear physics, and today we will know what is it. So, clicker, please. Clicker was charging. Thank you. And one of the most important elementary particles in cosmic rays and elementary particles for nuclear physics research is muons. What is muons? In fact, it's a part of cosmic rays. Cosmic rays is a flux of elementary particles that elementary particles that in fact covers all our surface. And if you look for this room, for example, and look at your body, every second about 100 muons are passing through your body. So that's the thing. Every second about 50 muons are passing through your body. And this is a constant flux that we can face on the surface of our planet. And what is muons in fact? Muons in fact is just, well, it looks like electron and it's interact like electron, but it's heavier in 200 times that an electron, and it means that this particle has excellent penetrating ability. From one hand, it gives a perfect response in any kind of detector, and from other hand, it can pass through a very deep places, for example, deep underground. It can go through hundreds of meters of rock, and you even can detect it in the 2 kilometers under the ice. So how it looks like? In fact, for physics, for theoretical physics, it looks like a process, for example, of decay of pi meson. It can look like that. Or this is a process like this muon decays into electron and couple of neutrino. And how it looks like by the eye. This is an example from bubble chamber. And here you can see like how in accelerator and pi meson, it goes like that. In magnetic field, it's rounded. And it decays in this small line. this green line is a muon that is decayed to positron and to neutrinos. Neutrinos are invisible to the eye since they don't interact with the detector, and here you can see how it looks like. This is a muon. Welcome. And this is a bunch of muons from accelerator also in such detector. It looks like tracks. So how to catch muons? So this is a very common dosimeter that you can buy in some special shop. And the idea is that if you place it on the table, the most hits that it will detect, it will be hits from muons. It's not from beta particles, it's not from alpha particles or gamma. The main radiational flux on our Earth's surface is a flux of cosmic ray muons. And from other hand, for high energy muons, we build huge detectors. And one of them is detector Ice Cube. Is placed on the South Pole, so in Antarctica. And this is really a masterpiece. It's situated, just imagine it, South Pole, Amundsen Scott Base, United States holds it. And there at the South Pole, there is a detector under 2 kilometers of ice, 2 kilometers. And it has a volume of 1 cubic kilometer. And it's filled with detectors of Cherenkov radiation coming from muons. And also, such detector detects muons, they go from atmosphere and gives response in it. And also, it can detect muons from underground that are produced by neutrinos. So this is, for comparison, an Eiffel Tower. And this is a South Pole. Just imagine how hard to get there. And this is a very typical detector for detection of atmospheric muons. It's called of muon hodoscope. So we can, you know what is telescope? Telescope is a device that detects radiation from some direction. Also, you can build multiple telescope or multi-directional telescope that can detect particles from several directions. And muon hodoscope is a detector that can detect all flux of muons from all directions and know from which direction each part came. How to use such detectors? You can make tomography or muonography using this flux. And this is a very bright example. So this is a water tower. And this water tower can be full or empty. And if you place such detector nearby and measure muon flux, you can see the difference in muon flux when it's full. When it's full, there is more matter, water, it stops muons, and it will decrease the number of muons. This is an example. Another example, another way how to detect it is to place muon detectors around our target, around the object we try to explore. And in this case is very precise, and this is called muon tomography. This is called muography. And the last way is how we detect features in pyramids. So I will talk it further. So this is a real example. This is placed in MIFI, and this is a really huge detector so that we hold on experimental complex Nevat. Experimental complex Nevat itself is a really bright detector that it consists of 2,000 tons of water in MIFI, and above it we have these 4 muon hodoscopes. It's called Uragan. The area of each detector is about 12 square meters. And so each detector can detect about 1,500 muons per second. It's a huge flux. And this is how it works. It detects flux and looks whether it's still or not. And here is the example. So this is a map of Moscow region. And this color corresponds to muon flux. If it's green, it means that it's common. That's the same flux that was yesterday. And here you can see change in this color. It means the decreasing number of muons. Muons are generated in the height about 15 or 20 kilometers. And if you see decreasing number, it means that something happens there. And this is an example of a large thunderstorm that was in the region. And in fact, what is the most important, that such thunderstorms can be detected in muons hours earlier than meteorology can detect this. So this is a bright example how we can detect it for weather and to save human lives, because large hurricanes happen in our region rather rarely, but they can kill people. And what is another important thing, that its name Uragan translates it's a translation to Russia word hurricane. Another example is how we detect cosmic weather. So what is magnetic thunderstorm? Magnetic thunderstorm comes when from sun we get large coronal mass ejections, is a huge clouds of plasma, and these huge clouds of plasma can stop cosmic rays from galaxy. And that means if such cloud comes closer to our planet, we can see decreasing number of particles. And this is an example how we can see such coronal mass ejection, this large cloud, as day before magnetic thunderstorm arrives. In fact, in other methods, we can detect it only about 40 minutes before it. So it's a very important instrument. So that was in MIFI. So also in other countries, in other regions, tries to use muons in real applied research. And this is volcanology. So this is a way how to find a moment when magma comes through the volcano. And if you place muon detectors from the different parts of rock, different parts of a volcano, you can find the decreasing flux of muons. And if it decreases, it means that something happens, that magma raise up. Another way is custom control. In the custom control, we use two pairs of detectors. One of them is situated above a track, and another pair is situated below it. And all the reflections of muons can be detected by these devices. And here is a response. So in such container, it's with lead bricks, a word is placed. And here is a response of detectors. So you can see that it can find even a word placed with lead bricks that can be detected by muons. What is important, it takes only several minutes to get such a picture. And why it's important also, because it cannot be lead, for example, it can be uranium, plutonium, or something like that. Another important application of muons is the control of atomic power plants. And this is a patient that our laboratory made for such research. And in fact, firstly, it was tried in Los Alamos National Laboratory when they made graphite blocks with uranium inside, and they saw how this uranium is placed inside this prototype of reactor. And the real application was at Fukushima inspection, when you know all this tragedy there, and the problems that is the position of nuclear fuel after this crash was unknown. Nobody knew whether this fuel is still in the reactor or maybe it's just made its way under the ground. And the muon detectors helped. So they placed detectors at the territory at about 200 meters from this reactor. They measured the flux of muons, and this is the response. So as you can see, there is no any fuel here inside. Not any muon is absorbed there. And this is a real example from our laboratory in MIFI. So last year we developed special detector that was made specially for muon tomography of Kalininsk power plant. And this is a building of it. And inside this building there is a nuclear reactor, water nuclear reactor inside this. This is how this detector looks like. In fact, it's about 3 meters in height. And this is a response, and you can see the lines of the nuclear building. And here is the place of nuclear reactor. And you can see that the most dense and heavy elements are placed here. Another thing, archaeology. In archaeology, you can use muon detectors to look through great large buildings. And the first try was in 1967. Nobel Prize Luis Alvarez made his experiment in the pyramid of Khufu. So in Russian it's Khefrena, the pyramid of Khefren. He placed detectors deep underground below the pyramid, and he tried to check does this flux really correspond to our predictions or not. And he didn't succeed. He found nothing there. Another try was in Central America, in the city of Teotihuacan, and below this pyramid also was placed a large detector of muons. And he tried to, well, look for the muon flux in these angles, in these zenith angles. And this detector also found nothing. But occasionally, the luck was leading by Japanese scientists, and they placed very small and simple muon detectors in the Queen's chamber below pyramid of Cheops. And the idea is that these detectors just placed without electricity, nothing about a year there, and they detected the full flux for years. It was a large statistics, and they found anomaly, and this is how it looks like in data. So the black line is expectation from simulation, and the red dots, it's real experimental data. And here you can see a huge excess, and that means that at one region of the pyramid there is a real void. And what is this? French physicists placed additional detectors, and they could find a special place that is situated above large gallery. So maybe if you were there, so you remember this huge gallery that you had going up to the stairs for a long time, and above this gallery there is another place, another void that is by the size is the same like it. So you can imagine how large is it. Another try was made last year, and they placed such detectors not in the Queen's room, but in the point of G here, and they found that also some additional room is below this place. And what is the funny thing that people from scientists that explore pyramids, that Egyptology is called, they have a lot of doubts about that. So what is the idea? Is that, I don't know, do you know why this chunk of Cheops has additional places above? There is the idea that pressure of blocks can destroy this room, and to prevent it, there is made special technical rooms above, and especially with these special blocks with the form of triangle, and this prevents this block from any crash. And in Egyptology, they say that additional for the main gallery, they think that there is also special place above with such a room, and it should be just to prevent this main gallery to be, well, to prevent it from high pressure of the rest of the pyramid. And another experiment was made in Pskov Pechorsky Monastery. This research was also several years ago, and it really gave a bright result in joint operation of Mises University and MIFI. And it helped to find new rooms in the combs of Pskov Pechorsky Monastery. This is how these detectors of muons looks like. And this is 3D geometry of combs below this monastery. And this green points is the unexplored rooms under this monastery, and this was found only because of these muon detectors. And finally, this is also the very last scientific results. In Canada, a physicist that was looking for years for caves, and they were looking for heavy elements, and they made this special detector. This is detector is also a muon detector, and they place it into this long how it's called, so holes, yes, okay, these long holes, and they say that such single hole can detect with these detectors can detect uranium deposits in the distance of about 500 meters, and even if you are lucky, 1.5 kilometers. And that means that it will help to find uranium deposits and save billions of dollars for drilling of such holes. So in conclusion, when I guess 100 years ago somebody, well, not somebody, but Victor Guess found cosmic rays, he never knew that it can be used in some applied research like electricity and something like that, or maybe neutrino. So we don't even know where our research will give its application. And muons is just a bright example of it. In fact, it covers maybe the most part of human work and life, and you can find its application everywhere, from pyramids to weather, to cosmic weather, and even to some growth of the food. So, if you like it, come to MIFI, look our muon detectors, and maybe you will be the one who made the new application of these bright particles. Thank you.
Thank you, Igor. Now it's time for questions. Who will start? Yes.
Здравствуйте. Скажите, каким образом устроен детектор и как проходит вообще механизм детектирования мюонов?
Okay. It's from the beginning, so we can. Yes. Okay. So the main types of detectors are scintillator detectors or gaseous detectors. So these are two types of detectors that are usually used for detection of muons. Also, we can use Cherenkov detectors, but it's a very large one. Okay, so what is dosimeter? It's a device that contains Geiger tube. So what is Geiger tube? It's just a cylinder with a wire inside, and in this wire you give a high voltage. It's about, well, maybe 500 volts per one tube. And this tube is filled with special gas. It's usually argon with CO2 and usually some alcohol there. And when a particle hits this tube, it ionizes the gas. When free electrons go to the electric field, it gets higher energy and it produces, well, a small lightning inside. And this lightning gives an electric signal that you can detect with common types of electronics. So the idea, a particle comes, it makes a small lightning inside, and you can detect it. Another way is to use scintillator detectors. Scintillator detector is some material that makes, when a particles go through it, it gives a flash of light inside. And for example, analogs of this muon horoscope consist of huge number of small scintillator parts, and when a particle hits it, there is a flash of light, and you can detect this flash of light with a photomultiplier or something like that. And when you know the points at which this flash of light was seen, you can place experimental points, and then with the methods of least squares, just make a line and calculate the direction of a particle, if it's clear.
Thank you. Next question.
You can ask me it outside, I will explain you in Russian. Okay.
Hello, my name is Lina, and I have the following question. Is NERVA the only center that has been studying the muons, or there are other centers somewhere in Russia or in the world?
muons.
Never is the only center which studies muons, or somebody else can do that.
Surely, Nevat in MIFI or in Russia or in the world. In the world, there is a huge number of detectors. So, for example, Ice Cube in the South Pole. So, and also, for example, this Pskov-Pechorovsk monastery, we made it with FIAN. And it's muons, in fact, is one of the most favorite particles for all physicists that work with elementary particles. It's the secondary particles, as I said, is very easy to detect, and it's very good at penetrating particle. It means that physicists from all over the world use detectors of muons to solve their problems and to find another particles, for example.
Any other questions?
Thank you very much.
Thank you, Igor. So we continue. Our next report will be devoted to the mechanism of excitation of atomic nucleus and numerous applications of this technology. And the report is Excite and Rule, how bound electrons help to accumulate the energy of nuclei. And please welcome Mr. Andrei Volodka, professor of Etmo University.
Thank you very much, dear friends, dear colleagues. So, good afternoon, everybody. So, I would like to talk about the nucleus and how to excite it. And for this aim, I would like to use bound or almost bound electrons. And first of all, I would like to give some motivation why it is so interesting and why we should study this. If we go back to history, and look for the atoms, when we manage to excite ensembles of atoms and quantum mechanically control them, then we invent so-called lasers and like current status of technology unthinkable without this kind of facilities. And another example is atomic clocks. The accuracy of the atomic clocks nowadays reach 10 to the minus 18, and this is somehow amazing accuracy. So these clocks loses only several seconds for the whole age of the universe. And another even more fascinating technology is the quantum computers, which will be, I hope, discussed tomorrow, and therefore I will not speak too much about this. Okay, but if we now go to the nucleus, what kind of new things or new ideas can bring us if we manage to make a quantum control on them? So first of all, it's a nuclear laser, and since the nuclear excitation being less influenced by the electric or magnetic field, so the nuclear laser will be much more narrow, and therefore we can use it for many other applications. So another thing is the nuclear clock. Yes, so the nuclear clock can reach accuracy 10 to the minus 21, so which is even 3 orders of magnitude better than our best atomic clocks. And another, which I point here out, it's energy storage and release. If we find and we know that there are a lot of metastable electromagnetic levels in nucleus, we can pump them up with, if we know some another level which is not a metastable, we can control in a control manner, pump it to this excited state, and then it's released to this metastable, and the energy is stored. And then, in order to release this energy, we can develop a trigger mechanism, like a triggering, and we trigger metastable state to some excited states, and then the energy will release. And so this is like a nuclear battery, and one can store the energy on the metastable electromagnetic levels of the nucleus. Let me give a small overview about the application of the nuclear clocks. So far, our GPS technology is based on the atomic clocks, and its accuracy reached to 1 to 10 meters, which is somehow limited by the accuracy of the atomic clocks. If we develop the GPS technology on the nuclear clocks, accuracy will be even centimeter to millimeter range, which allow us to make autonomous driving, freights, and companions trackings. So another is 3D gravity sensors. So the present accuracy is plus minus 2 centimeter, which allows us already to measure the change in gravity potential up to 2 centimeter. And if we do this technology on the nuclear clock, then we can investigate the monitor volcanic magma, how it's inside the Earth move. And another is tectonic plate movements, etc. Another interesting thing is the search for physics beyond the standard model, since we can suggest that our fundamental constant can vary in time, and if we know the clocks the frequency depends on this fundamental constant, we can search for variation of such a fundamental constants. So why we would like to make the nuclear excitation by the electrons? Since actually a lot of nuclear parameters was delivered us by the electrons or muons. For example, the proton radius is known from the hydrogen and from ionic hydrogen. So the instrument how we probe the nucleus is actually the electrons and the muons. Also, the magnetic moments and various moments or electric quadrupole moments of the nucleus is also known from muon or from electronic spectroscopy. And therefore, we can think that we can also use the electron to manipulate or to control the nucleus. For this, there are 3 mechanisms, or even 4, but I will mention today only 3 of them due to lack of time. So first one is the nuclear excitation by electron capture. So here we create a hole in the electron shell, and this hole is released or by the transition from the upper electron. And this, if the energy is exactly matching with the nuclear excitation energy, then we can see the transition by the electron with the simultaneous excitation of the nucleus. Another mechanism is the nuclear excitation by the electron capture, when the electron gets captured from the continuum, depicted here, to the bound state, and if again the energy is exactly matched to the nuclear excitation energy, then the nucleus gets excited. And the third mechanism is the nuclear excitation by 2-photon transition. If we have the electron which make a 2-photon transition, so one photon is emitted and another photon is exactly matched with the nuclear excitation, and the nucleus get excited. So I will review all of these 3 mechanisms, and let us start with the nuclear excitation by the electron transition. How is actually performed? So we shined with the X-ray and ionized one of the electron in the core shells, and then the hole is created, and this hole is then de-excited, yes, by the upper electron, and the nucleus get excited, and later we see the spontaneous emission of the nucleus. What kind of experiments and what kind of theory was measured and proposed for this mechanism? So actually there are several experiments in neptunium, gold, and osmium. So, but actually there is a problem in the theoretical description of this mechanism, and I will explain you later why. So in red I just pointed out the most trustable values. Okay, so here we should consider such kind of Feynman diagram. So the double line corresponds to the bound electron, and the bold line corresponds to the nucleus. And the electron and nucleus exchange the photons, and the excitation from the electron goes to the excitation of the nucleus. So the S matrix of such a process can be written in such a way, where we have a psi, capital psi is the nuclear wave function, and small psi is the electron wave function. Then if you make a multiple decomposition of this interaction operator, then we can come to this formula. And this formula shows that the electron and nuclear variables are decoupled, and then this integral can be replaced by the nuclear electromagnetic transition strength. And this actually, so I write it only for one electron, but if you have many electrons, so on this is wave function of a many electron system. And is this integral, if we have the many electron wave function, is rather difficult to calculate. And in order to improve our precision, we need to use rather high power computers in order to calculate this. And another difficulties is, another difficulties in this X-ray source. So usually the X-ray source was not so good, and therefore the width of this X-ray was rather large, and therefore it is difficult to describe the process of the whole creation. And if, as Yaroslav on the first panel explained us that there are a lot of synchrotrons of the next generation will be built, it produce much better sources for the X-ray, and we can see this process much more clearly. Okay, and what is the problem is with all this with this process, that this energy should be exactly the same as the energy of the nucleus, and therefore it is rather difficult to find such a system. We can overcome this problem if we look in another mechanism, so-called nuclear excitation by electron capture, where we can vary the kinetic energy of the electron. And adjusting the kinetic energy, we can find the energy or kinetic energy of the electron which exactly suits for the nuclear excitation. And this process actually was never observed, and we, together with our Chinese colleagues, whom are working on the heavy ion research facility in Lanzhou, proposed a mechanism and proposed a scenario how to observe it. So we generate the calculations and predict that there is a possibility to observe it. For example, for gadolinium, we find the nuclear excitation, which is around 60 kilo electron volts, and 1s binding energy is 59 kilo electron volts. So we need only the electron around 1 kilo electron volts of kinetic energy in order to match these energies. And then if we plot the radiative recombination signal, then we see that on the radiative recombination signal, we see the resonance peak, which exactly corresponds to the nuclear excitation. However, this was calculation for the exact electron energy, but if we include the distribution of the electron energy of the electron beam up to 1 MeV or 10 MeV or 10 MeV, this peak will be a bit smoothened. Okay, another mechanism is two-photon transition. So here, as you know, that the electron can undergo to the transition with the simultaneous emission of the two photons. So, and particular this kind of transitions scales with z, with the nuclear charge as z to the power of 6, and therefore one can expect that this kind of transition will be more dominant for heavy atoms or for heavy ions. And we find such a transition for helium-like ions, so it means that we have only 2 electrons left in the atom, so 1s, 2s, for example, with the total angular momentum 0, and then it's decays to the ground state only with the emission of the 2 photons. And because the 1 photon emission is completely forbidden. Okay, and what is the pattern? What is the spectrum of such emission? And we see actually that these photons can distribute energy between each other rather arbitrarily. Yes, so the distribution of the energy looks like this, like a parabola. And we see that the most probable that they will share energy, but it's also possible that that the energy will be different. Actually, this process is nicely observed in GSI, in Darmstadt, and therefore, together with our friends in Germany, we propose an experiment how to observe it for the nucleus. Yeah. So if we have a electron level in between, so if we have not a two-photon transition, just as it is, which is described by this curve, but if we have also like a level in between, then we have a cascade transition. So the photon the electron can first decay to this intermediate state and then to the ground state. And then we will have such kind of peaks, so one and another for the first and the second photon, and therefore this shape will be modified. So we will not have only this kind of shape, but also some peaks corresponding to this cascade. But however, if we have a nuclear level in between, the similar situation might happen. So the electron goes to the ground state with the emission of photon, and the second photon will excite the nucleus. So this is like will be a virtual photon which propagates the excitation to the nuclear degree of freedom. And then later the nucleus will decay with the emission of a photon. Okay, thank you. So we calculate such kind of cross-section and find that the rate of such kind of channel corresponding to the total rate is 10 to the minus 9. So it's rather predictable that the rate will be 10 to the minus 9 because it's for nuclear excitation by the electron transition. It's also similar order of magnitude. And also we propose how to detect this. So one can make a simultaneous measurement of such kind. So we have ion beam, and then we collide it with a gas gadget. We create the helium-like ion, and then the helium-like ion decay. And then we absorb the one photon, the second photon, and the ion. Also everything in the time coincidence. And then moving this detector, we can detect the nuclear decay. Also, we propose this mechanism also for detection of the thorium level. The thorium level, the first metastable state of thorium, it's around 8.5 electron volts, and this is a nice candidate for the nuclear clocks and for nuclear lasers, and therefore, like all community searching for this transition, and therefore we use our mechanism to search for this, propose for searching this transition as well. Okay, here we propose such kind of scheme where we excite the electron in some electron shell, and then it's decayed via two photon, and then excites the nucleus. And then, depending on what kind of energy for the nucleus we assume here, we propose to what kind of electron shell one has to excite the electron. Okay, and so here we propose the graph here. So with a different color, it is represented different levels to which one has to excite the electrons in order to search for the nuclear transition in this range. Okay, actually, I hope I'm in time, and that's all what I would like to tell you today. Thank you very much.
Thank you, Andrew. Let's move to the questions. Who will start? Yes, please.
Thank you very much for this presentation. That was really interesting. Sometimes it was quite understandable, sometimes really hard to understand, and I'm not deep into physics, but I'm interested in it. That's why I have a question about one experiment that you have shown us. It's about detection of decay. I'm interested where it is the slide before NEFP something. So I'm interested where do you use this, or do you use this like in practice, so not in theory?
Okay, together with the experimentalist, we design such kind of so this one or next one. So this one, I think, yeah. Yeah, together with the experimentalists, we propose such a scheme, but it's really difficult to measure. So we predict calculating the beam characteristics and number of helium-like ions created after the gas target. We suggest and simulate something about few hundreds photons coming from our mechanism. But in order to collect a good statistics, one have to have something like 1 month of beam time. And therefore, it is rather difficult to find such kind of beam time. And especially now in GSI, because it's under the reconstruction. But I hope at NICA, this kind of mechanism can be measured when it will be built. So therefore, yeah, so far it's not yet realized, this idea, but it's but we hope that this idea will be realized and we find this level. But what is nice that we can search with this mechanism level which is not yet known, because so far our scenario is proposed for the level, for the nuclear level which is known, but our mechanism shows that we can see some peaks and an unexpected place. And if we find this level or some signal, that means that we find a new level, a new nuclear level, which was not yet discovered.
Thank you. Next question, if there is any. Yeah, okay.
Thank you very much for the answer. And I have one more question. I'm wondering what makes nuclear clocks so accurate, and what is the main difference between atomic and nuclear clocks?
Okay, yeah, thank you very much for the question. So the electron cloud is rather large, yes, and therefore it's much more influenced by the electric and magnetic field, which is you cannot always screen this electric and magnetic field, and therefore you have always like a polarizability, like a thermal correction, which makes these nuclear clocks not so accurate. Yes, even you or everything under control, you still have this fluctuation fields. And since nucleus is rather small and it's much less affected by this electric and magnetic surrounding, therefore and also the energy levels are far away distributed in comparison with the electron. It makes that the nucleus is much difficult to disturb by any kind of environment, and that makes it much more accurate. Calculations say that by these 3 orders of magnitude. Yeah. You're welcome.
Thank you for the questions. Thank you, Andrew.
Yeah. You're welcome.
Yeah.
Thank you very much.
Thank you. So we are in the finishing line, and our concluding report will be dedicated to the stability and safety of the operation of nuclear reactor. And for this, it's necessary to know the current position of isotopic composition in this fuel. What are the methods? There are some, but not all the they are imperfect, but what are the most, I may say, accurate and effective? Let's talk about it. And the report is called Let's Look into the Working Reactor, how to find out the isotopic composition of the fuel by combining different approaches. And please welcome Mr. Alexander Nakhabov, candidate of the Technical Sciences, Associate Professor at Obninsk Institute of Nuclear Power Engineering of MIFI.
Okay, thank you very much for introduction. First of all, good evening, dear participants, dear colleagues. I know my report is the last one today, and I guess it will be last mile for you. I hope it will be not so hard. I will try to put my speech, my report in some short time, and you will have possibility to ask questions you're interested in. So, oh, great. Very famous scheme, I hope known for you. In my presentation, I will talk about nuclear reactors. Nuclear reactors, moreover, like usual ones, power nuclear reactors. And you see a traditional scheme of nuclear fission reaction for uranium-5, uranium-235. And it's, of course, basics. Very important during this fission, we will have byproducts. You see two nucleus really of new elements. On this slide you see krypton and barium. It's really like with mass probability we can find these elements, but in real life a lot of different possible isotopes can be produced during this decay, during this fission. And when we talk about isotopic content of nuclear fuel, what does it mean? Initially, for usual reactors with no specific like research reactors and so on, in usual power reactors nowadays majority of fuel options it's uranium dioxide, and initially we have about not more than 5% of uranium-5, uranium-8, and small amount of impurities. But when reactors start to work, start to operate, of course by time we have these fission products. All these fission products are unstable, and then these fission products will go through different kind of radioactive decay, alpha, beta, gamma, and so on. So actually in the end of campaign of reactor or during every time during operation, actually isotopic content of fuel is different. And really it's very important to know which isotopic content in some time. Of course, it's possible to operate without this fine knowledge, but it's very important for fuel cycle in general. Because, of course, there are a lot of different reasons from reactor physics point of view, because depending on isotopic content, we will have different features, different properties of reactor-like system. But, first of all, after operation, actually for final stage, for disposal, or if you're talking about very prominent, very prospective option for closed fuel cycle, anyway, radioactivity of spent nuclear fuel depends on, first of all, from this isotopic content. Because after operation, really, we have maybe 1%, maybe about this, of these byproducts. Really, after operation, we will have uranium-5, not 5%, but, for example, 2. We will have uranium-8 and small amount of byproducts. But this small amount of byproducts really, first of all, is responsible for high level of radioactivity. Of course, it's problems with reprocessing, with disposal, and so on. And of course, nowadays there is idea really to model, maybe, to model fuel cycle before. Before means, of course, we can choose some kind of fuel composition, and we try to choose really operation mode. But for power reactors, it's not so flexible like for research reactors, but nevertheless, it's possible. And question how to get information about this. I guess those of you who really specialized maybe like reactor physics or something near, of course, I guess you know basic equations in my presentation, really, I tried to avoid some equations or some very sophisticated graphs. So very a system of differential equation. And in this way, yes, first option to solve these equations. If we manage to solve this set of equations, really, we can get solution. As I know, it's possible not in all cases, first of all. And it's rather hard to get analytical solution. The next option, and you see some general idea here. There are some methods nowadays used in nuclear power plant as well. These methods are rather simple. These methods could be applied with no specific software, something like this. But in the same time, of course, these methods provides rather high error in calculations. But by the way, this error is enough for usual operation. For operation nuclear power plant, it's not critical because actually a lot of systems and so on and safety systems, it's possible. There are another option, like for example, this one I will use later. We can use different software. Modeling software, for example, Serpent, it's software based on Monte Carlo simulation of processes. In this way, we can really calculate, in fact, it's solving of this set of equations by numerical methods. We can get a very high accuracy solution. But these methods are very time consuming. So actually to model, for example, isotopic content of nuclear reactor like VVR, for example, for some moment of company, really it takes at least a dozen of hours, maybe several days, depend on computer. And idea of this work initially was to provide some methods really in the middle between practical methods, but with high error, and like simulation methods with very high accuracy, but time consuming. So of course, our desire to choose something between, in ideal, just to combine all advantages and so on. On this slide, you see photos. Photos, how it looks like. It's a fuel assembly of VVR reactor. Actually, the same from this point of view for VVR 1000 or VVR 1200 megawatts power units. So you see these tubes, a lot of thin tubes, there are fuel elements. Fuel elements really containing nuclear fuel, and altogether more than 300 fuel rods are combined in fuel assemblies. So one fuel assembly really is a unit to handle fuel, to reprocess, to load, and so on. And core, reactor core of VVR, real photo, you see. Core of reactor, and it's in dark, you can see really walls of reactor pressure vessel. So maximum enrichment, as I said, about up to 5%. And first of all, okay, we'd like to model data. About data, in my work, idea was to use methods like artificial intelligence or machine learning methods applying to this task. But when we talk about using some methods of data analysis, the main and very important issue about data. What is an initial data? This data will be used for training of algorithms and so on. Of course, when we talk about nuclear fuel, it will be great to have real data. Real data means real fuel unloaded from reactor after some time. Yes, there are, you know, maybe very special like hot cells, special laboratories where this fuel could be dismantled, and using, I guess, spectroscopy, different methods, we can get really isotopic content. But for power reactors, unfortunately, it can be made only after campaign. A campaign, at least between reloading, it should be 1.5 years for VVR 1200. Of course, it's a very big time spent between measures. For research reactors, maybe it's simpler, really, because for research reactors, fuel could be unloaded really in several days after operation. So in this case, we try to model this data. So our idea was, because real data is very hard to get, to produce, first of all, really, to produce means to measure. And second question, of course, is hard to get, because from Rosenergoatom company, really to get real results of spectroscopy for fuel, it's not so easy task, really. So idea was, okay, let's use modeling software like Serpent to model initial data. Moreover, of course, you can ask about some error which really will be added in this stage, because every modeling, of course, has some error. But error really rather small in this case. So data were modeled. You see like scheme of this numerical experiment. Actually, it's one fuel assembly, not core in general, only one fuel assembly with really 312 fuel elements, fuel rods. So you see yellow fuel elements, usual ones, uranium dioxide. Green, it's fuel elements with gadolinium. Gadolinium in nuclear reactors nowadays is used like burnable absorber, like very important element to improve finally quality of operation. And void circles, blank ones. Actually, it's guide tubes. Guide tubes, we can use different sensors inside or control rods and so on. So different data were modeled for different gadolinium concentration, like real ones, for different enrichment of fuel. And effective days, it means time of company. Effective day means one effective day when power unit really worked at 100% of power output. And finally, we managed to get this data. This moment was like not bottleneck here, but it's hard was because I said modeling is time consuming. So in this case, really it takes really several months to get this data. And the next stages were really like in data analysis. First of all, when we try to apply some neural networks, artificial neural networks, something like this, it's really, finally we can say, prohibited to use all data, because we should to divide data in training set. This set of data will be used for train algorithm and test data. In this case, as a model with validation. So initially on train data, we can train algorithm. On the test, testing during operation, during development of this method, and validation like really final set of data to provide for algorithm on the last stage. All these moments are provided just to increase accuracy, because otherwise our algorithm can be really with poor quality of work. And regression trees really were used here, like method of machine learning. This method very well known, like so-called classification and regression trees. So idea of this method, in this case we talk about regression. We really try to use some algorithm to predict function. Really, isotopic content is function, as usual, first of all, descending during the time. And idea of algorithm to use some predictor, some value, in special logic. And the main criteria is error. We try to find the best fit, maybe, law or function for our data. And totally, yes, method rather complicated. So this method, trees as usual, this method like neural networks and so on are implemented in many different software packages. So this method was applied to develop algorithm of prediction. Because idea is simple. We'd like to get on the input of this algorithm data, initial data. For example, in the start of company, we have this fuel with this isotopic content. Please give me data about this content, but after, I don't know, 1 month, 2 months, and so on. So it's our idea. Just to increase accuracy and to avoid errors, the so-called cross-validation method was used. What does it mean? When I said about dividing data in these sets, train, test, it means I will take all data, 70%, for example, training set, 30% testing. And I train data on the training set. But then 5 times I, with some randomly divided again, because every time in training set there are different data. In this way, we can avoid so-called overfitting of algorithm, and really we can increase significantly like robustness of this algorithm for possible changing in data. So according to this technique, for example, we see for 5-fold cross-validation that if we use simultaneously 3 different trees, combined results, we can get higher error, for example. But for 4, you see lowest level of round mean square error for data. So in this way, we can provide numerical experiment for different algorithms and choose the best one. And in this task, alongside the x-axis, you see really all isotopes which we tried to predict. Because yes, isotopic content could be different one, and totally there are a lot of different isotopes. But these ones are like most interested for us. So you see, yeah, first of all, uranium-5, basic isotope, and all others. You see neptunium, plutonium, and so on. So, and yes, during operation, amount of every isotope changing inside of fuel. So our task really to predict. And you see different models for different isotopes were used with different parameters of algorithm. For some isotopes, really, it's better to use 9-fold cross-validation. For some, really, it's not so serious, like for plutonium, for example. So actually, yes, finally, this method will be not so easy because really, for different isotopes, we use not one algorithm, but really like set of algorithms. Yeah, and results. In data mining, just to present results, very simple diagrams like this one, actual data and predicted. In ideal case, whole data should lie on the diagonal line. And if we see small like not fluctuation, but variation left-right, it means small error, really. It's a residual plot, the same, really, like error and this distribution of errors. Distribution, you know, we see it looks like normal distribution. It means okay, because as we know from theory, really it should be normal distribution of errors in usual case. This previous was for training set. Of course, it's, I guess it could be obvious if we use some data to train algorithm. As usual, of course, error on the training set is small because especially this data really were used to train. Testing data, this data really new. Algorithm know of this data before. And this data really new and really, as usual, on test set we can get rather high error. Anyway, higher than for training. But in this case, you can see it's really good results, not so distributed around. And for different isotopes, because there are different models, you see with star and dots, we have errors in test set with stars sign and errors in training set. Actually, we have only this one isotope is very specific, plutonium, because you see for training set really small, because it's, by the way, it's percentage 0.05. But for test set, it's really higher, significantly. And for uranium. For others, really results closer between. So it means, yes, of course, if we have a picture like this one with not so big difference, it means really our algorithm predict with good quality amount of this isotope in the fuel. So that's all briefly about this work. Finally, it was really it were 21 isotopes used. Moreover, besides of isotopes, we tried to predict a multiplication factor, but it really was like some byproduct of this work. So nowadays we have this algorithm, and if we talk about possible future development, directions of development, this work, of course, it's first of all producing more data, because initial modeled data were not so many data sets, because I said it's time consuming. And of course, in for us, really, it's interesting. This work was provided for VVR 1000 reactor, but for us, it's interesting to modify this work for research reactor. In Obninsk, there is Karpov Chemical and Physical Institution with research reactor, VBRC. For research reactor, really, to produce molybdenum, as I know, campaign is equal about 2 weeks. Of course, we really can try to get real data of analysis of fuel. In this case, of course, it will be more preferable because we will get some connection with real data and so on. And final task, yes, as I said initially, we can get lower error than traditional methods using right now, but at the same time, it will be really very quick because these methods, after developing of algorithm, it not takes a lot of time. Really, it's seconds on computer. That's all. So, if you have some questions, please ask. I will try to answer. Thank you very much for your attention.
Thank you, Alexander. Let's move to the questions, if there are any.
I guess all are very tired.
The last session, the
Yeah.
end of the day. Yes, you need a microphone because we have broadcasting online.
Directly in YouTube.
Okay, that's nice, thank you. My name is Elizaveta, and I would ask you, I have interest and to know which is the favorite and the most modern method for analyzing, because I can see a lot of kind of them, where maybe you can give a hint which is better to use. Thank you.
Do you mean which kind of methods, especially for this task?
For example, yeah, maybe something which can be like model, like for example, an engineer mission building, and I'm using construction, and I'm using model construction. Maybe there have something. I'm looking for something model.
Thank you very much. It's very good and very philosophic question, because especially in the data analysis, data mining, because you know, for example, nowadays in general, for example, there is ChatGPT neural network. Nowadays, very popular. I guess majority of people know nothing about how it works really inside, but it's impressive. Some photos, some results, and so on. Of course, there are a lot of different methods. First of all, I'm not sure it's possible to choose best one, because best one means really research. For example, in this work, regression trees were used. Of course, it's possible to use, for example, neural network. But first of all, of course, for engineers or for practitioner, of course, first of all, you will look at errors. You can say, guys, I don't like to know details. For me, it's important result. If this method is more with most accuracy, it's great. Maybe in many cases, this idea. But it's worth to know about in data analysis method. For example, this method, really, I can get some additional info why this result really was obtained. Because I really can get information which in this tree, like with this tree structure, which value was used and so on. For example, for neural network, and actually, as I know, it's like some initial drawback of this method, because neural network can be very powerful, but neural network, for example, really is black box. Like we have input, we have output, but if you will be asked why this result really was obtained, you can say, oh, this neural network, you could ask for here, and that's all. Yes, because nowadays in many cases, really people used combination. Moreover, some methods could be good in one mode, operation mode, for example, and another one in another mode. So yes, it's some process, continuous process, and in different stages. Yes, this method is better. Maybe tomorrow, next method will appear, and I guess it's interesting. Yeah. Yeah. Thank you.
Next question. Yes.
Yeah.
I want to ask about the decay heat of the spent fuel, specifically about the spent fuel of the plasma reactor in the world. Because I understand even after a reactor shutdown, the fuel is still going to produce some heat, right? So this spent fuel of this reactor, Yeah, how long is it going to take before it becomes stable? I want to know, is it somewhere in the storage facility still decaying, or maybe because I also know that there are studies for to produce the spent nuclear fuel.
Yeah, thank you very much. When I provided lecture in different countries all around the world, one of most popular questions about fuel, spent nuclear fuel, and about radioactive waste, for example. Yes, first of all, yes, it's known and it's connection with my topic, because after operation, it's some, really, we can say drawback, of course, nuclear power. Yes, after operation, instead of car, in car, after operation, you just get empty fuel tank and you need new fuel. That's all. Of course, we have some release in the atmosphere of something about this. Greta Thunberg, as usual, says something about pollutions and so on. But it's obvious. For nuclear, it's not the case. For my students, every time I say, oh, please imagine, you put something inside of reactor, fuel assembly. After 1.5 years, you will extract really big amount of fuel because due to swelling. Actually, geometrically, it will be more fuel than it was initially. Miracle. We produced electricity and fuel really looks the same. Of course, it's not miracle, isotopic content is other. And yes, these isotopes, first of all, are responsible for decay. In your question, it was part about, especially for first nuclear power plant. I comment right now. First of all, I remember some very simple rule from transport installations, not from power reactors, but for installations like on ships, on submarines, and so on. Very simple rule: a reactor should be cooled down during the same time as reactor worked before. For example, if reactor was in operation 4 months, you need 4 months to cool down this reactor, roughly. So, for first nuclear power plant, it's very simple. Nuclear power plant, first, if I remember right, was shut down finally in start of 2000s. Of course, like for every nuclear object, nuclear fuel really was unloaded. Was unloaded according standard technique after some time. And I don't know details, I guess this fuel was initially, as usual, stored in cooling pool on nuclear power plant. And when this fuel was transferred, I don't know, for reprocessing plant or something like this. So it's usual way. So nowadays, it's first slide. No, okay. Because in the start I had, this one. Yes, this question, your question, it's very important about fuel cycle. In many countries like United States, there is open fuel cycle, and it's supposed that fuel in finally just will be buried inside of special place. But nowadays, I'm not sure one country in the world really provided final version of this storage, because United States spent huge money for Yucca Mountain storage and so on. And yes, it's important. It's important which isotopes will be inside. And we should to have methods of calculation. But in Russian Federation, we first of all concerned about this closed fuel cycle because many kind of fuel could be reprocessed. We can extract from fuel uranium, unburned uranium-5. We can extract many isotopes. For example, in my presentation, alongside x-axis, you can show californium, I guess, different elements. 1 gram of californium, if I remember right, roughly maybe $1 million cost. So it's great. It looks great. Just extract. Only one problem: this fuel is very high radioactive. All operations, it should be special radiochemistry, and all operations with this fuel should be remoted with no direct human involvement. So it's problem. But this work, I think, is very important. Not right now for VVR maybe, but in our university in IATM, here in Obninsk, we met people from Rosatom, from Breakthrough project. Nowadays, new perspective reactors, one of favors in these projects, really to choose combination of parameters of reactor itself and fuel in such a way just to get some optimal isotopic content. Optimal means, for example, these isotopes will have half-lives not 10,000 years, for example, or million years, but really 1-200 years. In this case, really it will be revolution, because if we can significantly decrease radioactivity level, it will be great. So I guess this way, because this question, of course, is very big one. So thank you very much.
Thank you. Have 2 more questions.
People are real hero. Have questions in the end of day.
Good evening. My name is Lena, and I want you to ask about have you compared your results with real spent fuel and what is the amount of mistake? Because you work with the model, not real fuel, yes?
Yeah, thank you very much. It's a good question. And we asked this question for yourselves, sometime. With real data, no, because real data is very hard to get nowadays. Real data means really real fuel measured in some laboratory and so on. In this case, really, it was consultations with my colleagues because, of course, it's roughly, but from different research, really, I know some range of accuracy for Serpent simulation, because Serpent simulation really was compared with different fuel sets. Yes, and I know, for example, several % of possible errors. And my method, yes, directly, in my presentation, you saw on the last slide some errors. These errors were calculated especially for this. So really, yes, we have like composite error, one error between my work and simulated data, and another one, really unknown, between simulated data and real data. But I can some rough assessment about 1%, for example. But for me, it was important because anyway, this percentage is significantly better than for a simple method used nowadays. So this way.
And the final question.
Thank you very much. Good day, sir. You were my instructor in non-destructive testing in 2021, and it was an amazing course. So I would like to ask a question about the fuel integrity. Like during the research, is there any effort in trying to improve fuel integrity in the whole discussion about the nuclear fuel cycle?
Thank you very much. I don't know details of real, like, not spectroscopy just, but in general complex methods to get this isotopic content. Because from one side, fuel could be dismantled after some time, but of course not every fuel assembly and after really long time. As I know, spectroscopy of course could be made with hermetical fuel. Because for majority of fuel assemblies, it's usual story. There is no like defects during operation. Initially, yes, on this photo, all fuel rods are hermetically sealed. So actually, it's like zirconium tubes, very thin ones, just really welded from both ends. And moreover, there are special methods to detect possible like leak, because inside of these fuel rods are helium. So, as usual, I guess no effect on integrity, especially from this side. And because, you know, for spectroscopy, of course, I guess, due to walls, we have some disturbances maybe. But there is no need to dismantle these fuel rods just to measure isotopic content. So in this case, I guess no.
One more.
I guess last question. Others,
it was final, but one more.
In the corridor. Yeah, please.
Thank you. I wanted to ask, in this era where there's new technology such as reactors, which will be, some companies trying to introduce reactors which will be using liquid fuel. If in case we had maybe liquid nuclear fuel, would it show some fluctuations or maybe some changes in the isotopic composition after some time? And if those fluctuations will be, would Serpent help predict the different isotopic composition that will be in the spent nuclear fuel?
Thank you very much. If I understand right, you're talking about fuel, not liquid, like melted. Yeah, yeah, yeah. Thank you very much. I guess for this kind of reactor, if this reactor will be realized, this problem really will be not set in this formulation, because like melting salt reactor, for example, this idea is not new, as I know, many years. But idea, yes, that we really have not solid form of fuel, but really liquid ones. And this fuel really pumped through reactor core, for example, during operation. If I remember right, one of favors of this idea, for example, if I remember right, to provide permanent cleaning of this fuel. Because in this case, yes, we have fission reaction, we have byproducts, and of course these byproducts start to collect inside. But if you have liquid fuel, and I don't know, every several seconds or minutes this fuel really go out from reactor, so it's good idea, or let's try to provide some cleaning of this fuel really online. Not after operation, but right in time. But in these reactors, I heard on many conferences from my colleagues, my mention, personally mine, this reactor, if we talk about practical application, there are a huge number of like problems from engineering. Because first of all, we should to modify really some top-level IAEA documents regarding safety and so on. Because it means we, from the start, in the project, we try to say that nuclear fuel, highly radioactive, really will be outside of core, time by time. We should to provide protection, we should to provide this cleaning, but if we manage to make this cleaning, it means there is no serpent need. We say, oh great, we have uranium, every cycle, or every several cycles, we just remove some byproducts, and every moment we have like clean fuel. If we can provide in engineering this way, of course it will be great. But Serpent is just instrument, you know, like artificial intelligence in Serpent is just, modeling software, and this software could be used by you in different applications. So this problem, of course, will be modified, but anyway, it will be another problem, not this one, for melted salts, for example. So thank you.
Okay, thank you very much, Alexander.
Yeah, thank you.
So we are closing our scientific readings. And I would like to thank you, first of all, our dear speakers. It was great, it was challenging. And also our translators. I hope they survived. And our technical team and the audience. And I invite you to move to the main hall, where there will be a closing session of the day. So please, the forum still not finished for today. And please move to the main audience. And don't forget to take the program for tomorrow. And come tomorrow. Thank you very much.
Амбициозно берется за решение задач.